picture this. You're standing on a beach at sunset, waves lapping at your feet. The water that touches your toes has been on a journey billions of years in the making. That same water molecule might have once been inside a comet, frozen in the depths of space, or even part of the nebula that gave birth to our sun. Water is not just the stuff of life as we know it, it's cosmic. It's universal. And now, thanks to the James Webb Space Telescope, we know it exists on a world so close to us in cosmic terms that if the Milky Way were the size of the United States, this planet would be in the same neighborhood as your local grocery store. 26 light-years away. That's the distance to an exoplanet where JWST has detected something extraordinary: water vapor in its atmosphere. To put that in perspective, 26 light-years means that the light we're seeing from this world today left when you were 26 years younger. If you're watching this in 2024, that light began its journey in 1998. Bill Clinton was president. The iMac had just been released. Titanic was winning Oscars. And photons carrying the chemical signature of water were already racing toward Earth, just waiting for us to build an instrument sophisticated enough to catch them. Let me take you back to a moment that changed everything. It's December 25th, 2021, Christmas Day. While families around the world were opening presents and sharing meals, something unprecedented was happening in French Guiana. A European Ariane 5 rocket stood on the launch pad, and inside its payload fairing sat the most ambitious space telescope ever constructed. The James Webb Space Telescope, JWST for short, was about to begin a journey that would take it not to another planet, but to a point in space nearly 1 million miles from Earth, a location so precisely chosen that it would allow this marvel of engineering to peer deeper into the universe than any instrument before it. But here's what makes this story even more remarkable. JWST wasn't designed primarily to find water on nearby exoplanets. That was just one of its many objectives. This telescope was built to look back in time, to see the first galaxies that formed after the Big Bang, to watch stars being born in clouds of gas and dust, to study the atmospheres of planets around other stars. And yet, within its first year of operation, it had already detected water on a world that's practically in our backyard by cosmic standards. The exoplanet in question orbits a star you've probably never heard of unless you're an astronomer or an avid space enthusiast. But that's about to change. This star, this sun that another world calls home, sits in our stellar neighborhood. If you could travel at the speed of light, and let's be clear, you can't because physics won't let you, it would take you 26 years to get there. That might sound like a long time. You could raise a child from birth to college graduation in that span. But in the scale of our galaxy, which is 100,000 light-years across, 26 light-years is nothing. It's like comparing the distance from New York to Philadelphia with a trip from Earth to Pluto. Now, when we talk about detecting water on an exoplanet, we're not talking about seeing oceans through a telescope. We're not getting pictures of waves or coastlines. The way we detect water on distant worlds is far more subtle and, frankly, far more elegant. It comes down to light. Everything you've ever seen, every color you've ever perceived, every rainbow you've ever stopped to admire. It's all because of the way light interacts with matter. When light from a star passes through the atmosphere of a planet, the molecules in that atmosphere absorb specific wavelengths. Water vapor absorbs light at particular wavelengths in the infrared spectrum. And JWST is an infrared specialist. Think of it like this. Imagine you're trying to figure out what ingredients went into a cake just by looking at it from across the room. Impossible, right? But now imagine you have a tool that can analyze the aroma coming from that cake and identify every single molecule in that scent. That's essentially what JWST does with planetary atmospheres. When a planet passes in front of its star from our perspective, an event we call a transit, some of the star's light filters through the planet's atmosphere before reaching us. JWST captures that light, breaks it down into its component wavelengths using instruments called spectrographs, and looks for the unique fingerprints of different molecules. When the data came back showing the signature of water vapor, scientists around the world knew they were looking at something special. But let's pause for a moment and appreciate the sheer audacity of this achievement. We're talking about detecting water vapor in the atmosphere of a planet 26 light-years away. That planet is so far from us that if you pointed the world's most powerful laser at it, the beam would take 26 years to reach its target. And yet, we can tell you what molecules are floating in its sky. We can tell you about the chemistry of a world that no human will ever visit in our lifetimes, or our children's lifetimes, or probably even our children's children's lifetimes. That's not just science. That's poetry written in the language of physics. The discovery didn't happen overnight. It took months of observations, data collection, and analysis. Scientists had to account for countless variables. The star's own activity, for instance. Stars aren't perfect, unchanging orbs of light. They have weather in a sense. They have spots and flares and variations in brightness. All of that noise had to be filtered out to isolate the signal from the planet's atmosphere. Then there's the matter of Earth's own atmosphere, which, even though JWST is in space, can still affect observations in subtle ways during the data transmission process. Every photon had to be accounted for, every wavelength scrutinized. And here's something that should blow your mind. The amount of water we're detecting is vanishingly small compared to what we experience on Earth. We're not talking about oceans or even clouds in the sense that you understand them. We're talking about trace amounts of water vapor, molecules scattered through an alien sky. But the mere presence of water, in any amount, tells us something profound. It tells us that the same chemistry that makes life possible on Earth exists elsewhere in the universe. Water is made of hydrogen and oxygen, the first and third most abundant elements in the cosmos. The fact that they combine to form water wherever conditions are right isn't surprising. But confirming it, measuring it, proving it, that's what separates speculation from science. Now, you might be wondering, what kind of planet are we talking about here? Is it like Earth? Could we live there? Let me paint you a picture, and I'll warn you now, it's not going to be the paradise you might be imagining. This exoplanet is what we call a hot Neptune or a sub-Neptune, depending on who you ask. It's larger than Earth, possibly several times larger, but smaller than Neptune. Its mass puts it in that interesting middle category where we don't have a perfect analog in our own solar system. We have rocky planets like Earth and Mars, and we have gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune. But this planet, the something in between, the temperature on this world is likely scorching, at least by human standards. Because it orbits so close to its star, the day side of this planet is perpetually baked in stellar radiation. We're talking temperatures that could be hundreds or even over 1,000 degrees Celsius. At those temperatures, water doesn't exist as liquid. It exists as vapor, as steam, superheated and mixed with whatever other gases make up this planet's atmosphere. If you could somehow stand on the surface, assuming there even is a solid surface beneath all that gas, you wouldn't be admiring ocean views. You'd be vaporized instantly. But here's where it gets interesting. Just because this planet isn't habitable doesn't mean it's not important. In fact, it might be one of the most important discoveries in the search for life beyond Earth, precisely because of what it teaches us about planetary formation and evolution. You see, when we study exoplanets, we're not just looking for places where humans could set up shop. We're trying to understand how planets form, how they evolve, why some end up rocky and some end up gaseous, why some have water and some don't. Every exoplanet we study is a data point in the grand equation of planetary science. This particular planet, with its water vapor and its close orbit, tells us something about how water is distributed in planetary systems. It tells us that water isn't just a feature of planets in the habitable zone, that Goldilocks region where temperatures are just right for liquid water to exist. Water can exist in all sorts of environments, in all sorts of forms. It can be in the scorching atmosphere of a hot Neptune. It can be frozen on the surface of Europa, one of Jupiter's moons. It can be liquid on Earth. It can be in the clouds of Venus, mixed with sulfuric acid. The universe is diverse, and water is apparently everywhere. Let me take you deeper into the technology that made this discovery possible, because JWST is not just another space telescope. It's a revolution, The Hubble Space Telescope, which has been our eye in the sky for more than 3 decades, is a marvel in its own right. But Hubble primarily observes invisible and ultraviolet light, the same light your eyes can see plus a little bit beyond. JWST, on the other hand, is an infrared observatory. It sees the universe in heat. It detects the warmth of distant objects, the glow of stars hidden behind dust clouds, the faint thermal emissions from exoplanet atmospheres. Why infrared? Because the universe is expanding, and as it expands, light gets stretched. The light from the most distant galaxies, the ones that formed just a few 100 million years after the Big Bang, has been stretched so much that it's shifted from visible light into the infrared. This is called redshift, and it's one of the most important concepts in cosmology. But infrared is also perfect for studying exoplanets because planets emit most of their detectable light in the infrared spectrum. They're warm objects, and warm things glow in the infrared. JWST's primary mirror is over 21 feet in diameter, made up of 18 hexagonal segments coated in gold. Gold is an excellent reflector of infrared light, and those 18 segments work together to collect as many photons as possible from the faintest, most distant objects in the universe. Behind that mirror is a suite of instruments that would make any scientist weep with joy. There's the near-infrared camera NIRCam, which captures stunning images of galaxies and nebulae. There's the near-infrared spectrograph NIRSpec, which can analyze the light from hundreds of objects simultaneously. There's the mid-infrared instrument MIRI, which operates at even longer wavelengths and can see through dust clouds that block visible light. And there's the fine guidance sensor and near-infrared imager and slitless spectrograph, or FGS-NIRIS for short, which is specifically designed to study exoplanet atmospheres. All of these instruments have to be kept incredibly cold to function properly. Infrared light is heat, and if the telescope itself were warm, it would be like trying to see stars at night while standing next to a bonfire. So JWST has a sun shield the size of a tennis court, made of 5 layers of material thinner than a human hair. This shield blocks the heat from the sun, the Earth, and the Moon, keeping the telescope at a frigid minus 370 degrees Fahrenheit. That's cold enough to turn air into a liquid if you could somehow transport it there. The journey to get JWST to its observing location was nail-biting. The telescope had to be folded up like origami to fit inside the rocket fairing. Once in space, it had to unfold itself in a precise sequence over the course of 2 weeks. Every step had to work perfectly. There were no second chances, no service missions like the ones that saved Hubble when its mirror turned out to be faulty. If anything went wrong, JWST would be a $10 billion piece of space junk. The tension at NASA was palpable. Engineers who had worked on the project for decades watched as their creation deployed itself a million miles away, where no human could reach it to fix a problem. But it worked. Every latch clicked, every panel unfolded, every mirror segment aligned. And on January 24, 2022, JWST arrived at its destination, the second Lagrange point, or L2. This is a special location in space where the gravitational pulls of the Sun and Earth balance out in such a way that JWST can orbit the Sun while staying in roughly the same position relative to Earth. It's an elegant solution to a complex problem, and it allows the telescope to have a stable, cold environment with a clear view of the universe. The first images from JWST were released to the public on July 12, 2022, and they were breathtaking. Galaxies billions of light-years away appeared in stunning detail. A star-forming region called the Carina Nebula revealed structures never seen before. The atmosphere of an exoplanet was analyzed with unprecedented precision. The world watched in awe as JWST delivered on its promise to revolutionize our understanding of the cosmos. But back to our planet 26 light-years away. When the data showing water vapor came in, it wasn't just a single observation. Scientists conducted multiple transits, watching the planet pass in front of its star again and again. Each transit provided more data, more photons, more pieces of the puzzle. The signal for water vapor appeared consistently. The wavelengths matched what we expect from H2O molecules absorbing infrared light. There was no doubt. This planet had water in its atmosphere. Now, I want to take you on a thought experiment. Imagine you're standing on a hill on this distant exoplanet, somehow protected from the heat and the hostile environment by some futuristic spacesuit. You look up at the sky. What would you see? The star this planet orbits is smaller and cooler than our sun. It's what we call a red dwarf, or more precisely, an M-dwarf star. These stars are the most common type in the galaxy, making up about 70% of all stars. They're dimmer than our sun, which means planets have to orbit much closer to them to receive enough warmth. That's why this exoplanet is so close to its star, and why it's so hot. From the surface of this planet, the star would loom large in the sky, maybe several times larger than the sun appears from Earth. It would glow with a deep orange or red hue, casting an eerie light over the landscape. If there are clouds of water vapor, they would be unlike any clouds you've seen on Earth. They might be laced with other compounds, sulfur dioxide, methane, who knows what else. The sky might be a strange color, maybe pink or orange or purple, depending on how light scatters through the atmosphere. And if you looked carefully, if you had a powerful enough telescope, you could find a small, pale blue dot in the distance. That would be Earth, our home, 26 light-years away, visible as a faint point of light in the alien sky. From that vantage point, we would be the exoplanet. We would be the world that someone else might be studying, wondering if it has water, wondering if it could harbor life. This brings me to one of the most profound questions in all of science. Are we alone? For all of human history, we've wondered if there's life beyond Earth. Ancient peoples imagined gods and spirits in the sky. In the modern era, we've speculated about Martians and UFOs and alien civilizations. But it's only in the last few decades that we've had the technology to actually search for answers. And the discovery of water on exoplanets is a crucial step in that search. Water is essential for life as we know it. Every living thing on Earth, from the smallest bacteria to the largest whale, needs water to survive. Water is a solvent, meaning it can dissolve a wide range of substances, which makes it perfect for the chemistry of life. It's also a stable liquid over a wide range of temperatures, thanks to the properties of the hydrogen bonds between its molecules. When we look for life beyond Earth, we follow the water. Where there's water, there could be life. But let's be clear, finding water on an exoplanet doesn't mean we've found life. It means we've found a necessary ingredient for life, at least as we understand it. The next steps are to search for other biosignatures, signs of life, in the atmospheres of exoplanets. Things like oxygen in large quantities, which on Earth is produced by photosynthetic organisms, or methane combined with oxygen, a disequilibrium that suggests active biology, or phosphine, a gas that's hard to produce without life. JWST is capable of detecting these molecules if they're present in sufficient quantities. The exoplanet 26 light-years away, despite its water vapor, is unlikely to host life. The temperatures are too extreme, the radiation too intense. But it's a stepping stone. It's proof that JWST can detect the chemical composition of exoplanet atmospheres. And if it can do it for this planet, it can do it for others, potentially including rocky planets in the habitable zones of their stars, where conditions might be just right for life to emerge. There's another layer to this discovery that's worth exploring: the sheer number of exoplanets we've found. When I was a kid, we didn't know if planets existed around other stars. It was a reasonable assumption. After all, if our sun had planets, why wouldn't other stars? But we had no proof. That changed in 1992 when astronomers discovered planets orbiting a pulsar, and then in 1995 when the first planet around a sun-like star was confirmed. Since then, we've discovered thousands of exoplanets. The Kepler Space Telescope alone found over 2,600 confirmed exoplanets before it ran out of fuel in 2018. The count is now well over 5,000, and we're just getting started. The diversity of these worlds is staggering. We've found hot Jupiters, gas giants that orbit their stars in just a few days. We've found super-Earths, rocky planets larger than Earth but smaller than Neptune. We've found rogue planets drifting through space without a star. We've found planets in binary star systems, where two suns share the sky. We've found planets with orbits so eccentric they swing from freezing cold to scorching hot over the course of a single year. Every new discovery challenges our understanding of how planets form and evolve. And now, with JWST, we're entering a new era. We're not just finding planets. We're studying them in detail. We're analyzing their atmospheres, their temperatures, their compositions. We're beginning to understand what makes each world unique. The discovery of water vapor on this nearby exoplanet is just the beginning. In the coming years, JWST will observe dozens, maybe hundreds of exoplanets. Each one will add to our growing library of alien worlds. Each one will teach us something new about the universe. Let me tell you about the star itself, because stars are fascinating. This particular red dwarf is relatively quiet, which is good news for any planets in its system. Some red dwarfs are incredibly active, flaring up with violent bursts of radiation that could strip away a planet's atmosphere over time. A quieter star means a more stable environment, which is better for retaining an atmosphere and, potentially, for life. This star is also relatively old, billions of years old, which means its planets have had time to evolve and change. Red dwarfs live for trillions of years. That's not a typo, trillions with a T. Our Sun, a medium-sized yellow dwarf, will live for about 10 billion years total. It's currently about halfway through its life. But red dwarfs burn their fuel so slowly that they'll outlive every other type of star. Long after our Sun has swelled into a red giant and then collapsed into a white dwarf, red dwarfs will still be shining. If life ever emerges on a planet around a red dwarf, it will have eons to evolve and flourish. The universe's far future belongs to red dwarf systems. But there's a catch. Red dwarfs emit most of their light in the infrared, which means less visible light reaches their planets. Any photosynthesis would have to be adapted to use infrared light. Also, planets in the habitable zone of a red dwarf are so close to their star that they often become tidally locked, meaning one side always faces the star and the other side is in perpetual darkness. Imagine a world where one hemisphere is an endless scorching day and the other is a frozen eternal night. The only habitable regions might be in the twilight zone, the narrow band where day and night meet. These are the kinds of questions that keep astrobiologists awake at night. When we think about life on other worlds, we have to think about all the ways it might differ from life on Earth. We have to imagine ecosystems that thrive in darkness, organisms that breathe gases we'd find toxic, chemistry that operates at temperatures that would kill us instantly. The discovery of water on this exoplanet reminds us that the universe is full of possibilities, but it also reminds us how much we still have to learn. One of the most exciting aspects of JWST's capabilities is its ability to observe exoplanet atmospheres during transits with incredible sensitivity. When a planet passes in front of its star, only a tiny fraction of the star's light filters through the planet's atmosphere. We're talking about a difference of maybe a few hundredths of a percent in the star's brightness. JWST can detect those minute variations and extract a wealth of information from them. It's like listening to a whisper in a thunderstorm and understanding every word. The instruments on JWST are so sensitive that they can detect the presence of individual molecules based on their spectral signatures. Water vapor has a distinctive pattern of absorption lines in the infrared spectrum, and those lines showed up clearly in the data from this exoplanet. But water wasn't the only thing detected. There were hints of other molecules too, possibly carbon dioxide, maybe methane, perhaps even more exotic compounds. Each molecule tells part of the story of this planet's history and composition. Think about what this means for future observations. If JWST can detect water on a hot, inhospitable world 26 light-years away, imagine what it might find on a more temperate planet. There are thousands of exoplanets in our cosmic neighborhood, and some of them are in their star's habitable zone. Some of them might have oceans, weather systems, maybe even continents. JWST could analyze the atmospheres of these worlds and look for signs that they're not just habitable, but inhabited. Of course, we have to be realistic about the challenges. Not every exoplanet is oriented in such a way that we can observe transits. The geometry has to be just right, with the planet's orbit aligned edge-on from our perspective. Only a small fraction of exoplanets meet this criterion. But even so, there are hundreds of potential targets for JWST to study, and new telescopes are being planned that will expand our capabilities even further. The next generation of ground-based observatories, with mirrors 30 meters or larger in diameter, will be able to directly image some nearby exoplanets and study their atmospheres without needing to wait for transits. The discovery of water on this exoplanet also highlights the importance of follow-up observations. The initial detection was exciting, but scientists didn't stop there. They conducted more observations to confirm the finding, to rule out alternative explanations, to gather as much data as possible. In science, one measurement is interesting, but multiple measurements are convincing. The more data you have, the more confident you can be in your conclusions. And speaking of conclusions, let's talk about what this discovery means for the search for extraterrestrial intelligence, or SETI. For decades, SETI researchers have been listening for radio signals from alien civilizations, scanning the skies for any sign that we're not alone. So far, we haven't heard anything conclusive. But the discovery of water on exoplanets and the growing catalog of potentially habitable worlds gives us more targets to point our radio telescopes at. If there's life out there, it's more likely to be on a planet with water than on a dry, lifeless rock. There's also the question of technosignatures, signs of advanced technology. While biosignatures tell us about the presence of simple life, technosignatures could reveal the existence of intelligent civilizations. Things like atmospheric pollution, which might seem like a strange thing to search for, but on Earth, certain chemicals in our atmosphere are produced primarily by industrial processes. If we detected those chemicals on an exoplanet, it could be a sign of technology. Or light pollution. Imagine if a planet had cities on its night side that were bright enough to be detected from light years away. These are speculative ideas, but they're within the realm of possibility. Let me take you even deeper into the science of spectroscopy, because this is the technique that makes all of this possible. Spectroscopy is the study of how light interacts with matter. Every element and every molecule absorbs and emits light at specific wavelengths, creating a unique pattern like a fingerprint. When you pass light through a prism or a diffraction grating, it spreads out into a spectrum, a rainbow of colors. But if you look closely, you'll see dark lines or bright lines in that spectrum. Those are absorption and emission lines, and they correspond to specific transitions in the energy levels of atoms and molecules. For example, hydrogen, the simplest and most abundant element in the universe, has a set of absorption lines in the visible spectrum known as the Balmer series. When you see those lines in the spectrum of a distant star or galaxy, you know there's hydrogen there. The same principle applies to molecules like water. Water vapor absorbs infrared light at wavelengths of about 1.4 micrometers, 1.9 micrometers, and 2.7 micrometers, among others. When JWST detected those absorption features in the light from the exoplanet star during a transit, it was seeing the signature of water molecules in the planet's atmosphere. But interpreting spectra isn't always straightforward. The atmosphere of an exoplanet is a complex place, with different layers at different temperatures and pressures, potentially with clouds and hazes that can obscure the spectral features. Scientists use sophisticated models to simulate how light would interact with different atmospheric compositions, and then they compare those models to the observed data. It's a process of trial and error, of tweaking the models until they match the observations as closely as possible. In the case of this exoplanet, the model suggested that water vapor is mixed throughout the upper atmosphere, possibly along with other gases. The concentration of water is still being refined as more data comes in, but the initial estimates suggest it's a significant component of the atmosphere. This is consistent with what we'd expect for a planet of this size and temperature. Water is abundant in the universe, and if the conditions are right for it to exist as vapor, it will be present. Now let's talk about the broader context of this discovery. The detection of water on this exoplanet is part of a larger program to study nearby planetary systems. Astronomers have compiled a list of priority targets for JWST, stars that are close to us, bright enough to be observed in detail, and known to have planets. These are the low-hanging fruit, the systems where we're most likely to learn something new. The exoplanet in question was high on that list because of its size, its orbit, and the brightness of its host star. Over the next few years, JWST will observe many more exoplanets in this catalog. Some of them will be hot Jupiters or hot Neptunes like this one. Others will be smaller, rocky planets more similar to Earth. Each observation will add to our understanding of planetary atmospheres, of the distribution of water and other volatiles, of the conditions that might allow life to arise. It's a methodical process, one planet at a time, but it's already yielding extraordinary results. There's also an important lesson here about the value of patience and persistence in science. JWST took more than 20 years to develop, from the initial concept studies in the 1990s to the launch in 2021. Cost billions of dollars. There were delays, budget overruns, and moments when it seemed like the project might be canceled. But the scientists and engineers involved never gave up. They kept pushing forward, solving one technical challenge after another, because they believed in the mission. And now, their efforts are paying off in discoveries like this. The detection of water on this exoplanet is also a reminder of how far we've come in the field of astronomy. 100 years ago, we didn't even know that other galaxies existed. We thought the Milky Way was the entire universe. Then Edwin Hubble showed that the fuzzy nebulae we could see through telescopes were actually distant galaxies, each containing billions of stars. 50 years ago, we didn't know if planets existed around other stars. Now we've found thousands of them. 20 years ago, we couldn't analyze the atmospheres of exoplanets. Now we can tell you what gases are present in the sky of a world 26 light-years away. The pace of discovery is accelerating, and it's thrilling to be alive at this moment in history. Let me also address a common misconception. When we say a planet is in the habitable zone, that doesn't mean it's Earth-like or capable of supporting life. The habitable zone is simply the range of distances from a star where temperatures are right for liquid water to exist on a planet's surface, assuming the planet has a suitable atmosphere and other conditions. Mars and Venus are both technically in or near the habitable zone of the Sun, but Mars is too cold and has too thin an atmosphere, while Venus is a hellscape of crushing pressures and sulfuric acid clouds. Being in the habitable zone is necessary but not sufficient for habitability. The exoplanet we're discussing is well outside the habitable zone of its star. It's too close, too hot. But that doesn't diminish the significance of finding water there. If anything, it raises interesting questions about how water gets distributed in planetary systems. Did this planet form farther out where water ice was abundant and then migrate inward? Or did water get delivered to it later by comets and asteroids? These are active areas of research, and every new discovery provides clues. One of the most exciting prospects for future research is the study of Earth-sized planets in the habitable zones of nearby stars. There are several candidates within a few dozen light-years of Earth. Proxima Centauri, the closest star to the Sun at just 4.2 light-years away, has a potentially habitable planet called Proxima Centauri b. The TRAPPIST-1 system, about 40 light-years away, has 7 Earth-sized planets, 3 of which are in the habitable zone. These are prime targets for JWST and future telescopes. If we can detect water vapor, or better yet, oxygen and methane together on any of these worlds, it would be a game changer. But let's not get ahead of ourselves. Even if we detect biosignatures on an exoplanet, confirming that they're actually signs of life will be a monumental challenge. We'll need multiple lines of evidence, observations from different instruments and telescopes, and careful analysis to rule out false positives. It's going to take time, probably decades, before we can say with confidence that we've found life beyond Earth. But the journey is just as important as the destination, and every step forward is a victory for human curiosity and ingenuity. The discovery of water on this exoplanet also has philosophical implications. It reminds us that Earth is not special, at least not in the sense that we once believed. For most of human history, we thought Earth was the center of the universe, that everything revolved around us. Copernicus showed that the Earth revolves around the Sun. Hubble showed that the Sun is just one of billions of stars in one of billions of galaxies. And now we're learning that Earth is just one of potentially billions of planets with water and possibly life. This is both humbling and exhilarating. Humbling because it puts our place in the universe into perspective. Exhilarating because it means we're part of something much larger than ourselves. There's a concept in astrobiology called the Copernican principle, which states that there's nothing special about our location in the universe. If life arose on Earth and if the conditions for life are common, then life should be common throughout the universe. This doesn't mean we'll find intelligent civilizations on every other planet, but it does suggest that microbial life, at least, might be widespread. The discovery of water on exoplanets supports this idea. Water is common. The building blocks of life are common. The universe is a fertile place. Of course, there's also the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If life is common, and if intelligent civilizations are common, why haven't we seen any evidence of them? There are many possible answers to this question. Maybe intelligent life is rare. Maybe civilizations tend to destroy themselves before they can colonize the galaxy. Maybe the galaxy is so vast that we simply haven't encountered anyone yet. Or maybe we're looking in the wrong places or in the wrong ways. These are profound questions, and we may not have answers in our lifetimes. But the search for water and other biosignatures on exoplanets is bringing us closer to understanding our place in the cosmos. Let me take a moment to talk about the people behind this discovery. Science is often portrayed as the work of lone geniuses, but in reality, it's a collaborative effort involving hundreds or even thousands of people. The team that analyzed the JWST data on this exoplanet includes astronomers, physicists, engineers, data scientists, and more. They come from institutions all over the world, and they bring different perspectives and expertise to the table. Some of them have been working on this project for years, poring over data, refining models, writing papers. Their dedication and hard work are what make discoveries like this possible. And let's not forget the engineers who designed and built JWST. Every component of the telescope, from the gold-coated mirrors to the sun shield to the instruments, was meticulously crafted to perform flawlessly in the harsh environment of space. The level of precision required is mind-boggling. For example, the mirrors had to be aligned to within billionths of a meter, and the temperature of the instruments had to be kept stable to within a fraction of a degree. The engineers spent years testing and retesting every system, running simulations, preparing for every possible scenario. Their efforts paid off when JWST launched successfully and deployed perfectly. There's also the team of mission controllers who operate JWST on a daily basis. They plan observations, monitor the telescope's health, and troubleshoot any issues that arise. It's a 24/7 job, and it requires constant vigilance. Every observation has to be carefully scheduled to maximize the science return while managing the telescope's resources. The controllers work closely with the science teams to prioritize targets and allocate observing time. It's a delicate balancing act, and they make it look easy. The discovery of water on this exoplanet is the result of all of these people working together toward a common goal. It's a testament to what humanity can achieve when we collaborate and push the boundaries of what's possible. And it's a reminder that science is not just about making discoveries. It's about the process, the journey, the people who dedicate their lives to understanding the universe. Now, let's talk about the future. What's next for JWST and the study of exoplanets? The short answer is a lot. JWST is just getting started. It's expected to operate for at least 10 years, possibly longer if its fuel lasts. During that time, it will observe thousands of objects, from nearby exoplanets to the most distant galaxies. Each observation will contribute to our growing understanding of the universe. In the realm of exoplanet science, JWST will focus on characterizing the atmospheres of a diverse range of planets. Hot Jupiters and hot Neptunes will continue to be observed because they're easy targets. They're big, they transit frequently, and they produce strong signals. But JWST will also turn its attention to smaller, cooler planets, the ones that are more like Earth. These observations will be more challenging, requiring longer integration times and more sophisticated data analysis, but the payoff could be enormous. Finding water, oxygen, or other biosignatures on a rocky, temperate exoplanet would be one of the greatest discoveries in the history of science. Beyond JWST, there are other missions in the pipeline that will complement and extend its work. The Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy, is scheduled to launch in the mid-2020s. Roman will have a field of view 100 times larger than Hubble's, allowing it to survey large swaths of the sky and discover thousands of new exoplanets using gravitational microlensing and other techniques. It will also be able to directly image some giant exoplanets, providing a different perspective on these worlds. On the ground, the next generation of extremely large telescopes is under construction. The Extremely Large Telescope in Chile, with a mere 39 meters in diameter, will be the largest optical telescope in the world when it's completed. The 30-meter telescope in Hawaii and the Giant Magellan Telescope in Chile are also in development. These telescopes will have the resolution and sensitivity to directly image exoplanets and study their atmospheres in detail. They'll complement JWST by observing invisible and near-infrared wavelengths, providing a more complete picture of exoplanet atmospheres. There are also proposals for future space missions specifically dedicated to finding and characterizing Earth-like exoplanets. Concepts like the Habitable Exoplanet Observatory, or HABEX, and the Large UV Optical Infrared Surveyor, or LUVOIR, would use advanced coronagraphs or star shades to block the light from stars and directly image the planets orbiting them. These missions are still in the planning stages, but they represent the next frontier in exoplanet science. Imagine being able to see the continents and oceans of a planet orbiting another star, or to detect the seasonal changes in its atmosphere as it moves through its year. That's the goal. Closer to home, there's also the possibility of studying the moons of Jupiter and Saturn for signs of life. Europa, Enceladus, and Titan are all considered potentially habitable, with subsurface oceans or lakes of liquid methane. NASA's Europa Clipper mission and ESA's JUICE mission will explore these moons in the coming years, searching for evidence of the conditions that could support life. If life exists in our own solar system beyond Earth, finding it would have profound implications for the prevalence of life in the universe. But let's return to our exoplanet 26 light-years away. What does the future hold for this particular world? Will we continue to study it, or will it fade into the background as we move on to new targets? The answer is both. This planet will remain an important benchmark for understanding hot Neptunes and the presence of water in extreme environments. It will be observed again with different instruments and at different wavelengths to refine our understanding of its atmosphere. But JWST has a universe to explore, and there are countless other worlds waiting to be discovered and characterized. One of the most intriguing questions about this planet is whether it has any moons. Large planets often have moons, and some of those moons can be quite interesting in their own right. In our solar system, moons like Europa, Enceladus, and Titan are among the most promising places to search for life. Could this exoplanet have a moon with a subsurface ocean, warmed by tidal forces from the planet's gravity? It's possible, but detecting exomoons is incredibly difficult. They're small, and their effects on the light from the parent star are subtle. Still, astronomers are working on techniques to find them, and JWST's sensitivity might make it possible to detect the largest exomoons around nearby planets. Another question is whether this planet has a magnetic field. Magnetic fields are important for protecting a planet's atmosphere from being stripped away by stellar wind. Earth's magnetic field, generated by the motion of molten iron in its core, shields us from the sun's radiation. Mars, which lost its magnetic field billions of years ago, has had much of its atmosphere eroded away by the solar wind. For a planet orbiting close to its star, especially a red dwarf that can have powerful flares, a magnetic field could be crucial for maintaining an atmosphere over long timescales. Detecting magnetic fields on exoplanets is another area of active research, and it's something that future observations might be able to address. The study of exoplanets is also shedding light on the formation and evolution of our own solar system. By observing planets at different stages of development, around stars of different types and ages, we're piecing together a more complete picture of how planetary systems form. We now know that planet formation is a messy, chaotic process. Planets migrate inward and outward, collide with each other, get ejected from their systems. The neat, orderly arrangement of our solar system is just one possible outcome out of many. Understanding this diversity helps us appreciate how lucky we are to live on a stable, habitable planet. There's also the question of how common water is in the universe. We know it's abundant. Hydrogen and oxygen are among the most common elements, but the form it takes and where it ends up depends on the conditions in each planetary system. Water can be locked up in ice on the surfaces of distant moons. It can be vapor in the atmospheres of hot planets. It can be liquid in the oceans of temperate worlds. By studying water in all its forms across different types of planets, we're learning about the cosmic water cycle, if you will, how water moves through the galaxy and ends up on worlds like Earth. And speaking of Earth, let's take a moment to appreciate our own planet. Earth is a water world, with oceans covering more than 70% of its surface. But water isn't just on the surface. It's in the atmosphere as vapor, forming clouds and driving weather. It's in the ground as groundwater that feeds rivers and lakes. It's even in the mantle, deep beneath the crust, carried down by subducting tectonic plates. Water has shaped Earth's geology, its climate, its biology. Without water, Earth would be a barren, lifeless rock. But Earth's water didn't start here. Most of it was delivered by comets and asteroids during the early history of the solar system, in a period called the Late Heavy Bombardment about 4 billion years ago. These icy bodies, originating from the outer solar system, crashed into the young Earth, bringing water and organic molecules. It's a process that likely happens in many planetary systems, seeding inner planets with the ingredients for life. The discovery of water on the exoplanet 26 light-years away suggests that similar processes are at work throughout the galaxy. Now, let's talk about the cultural impact of discoveries like this. When the first exoplanets were discovered in the 1990s, it captured the public's imagination. People began to realize that planets around other stars weren't just science fiction, they were science fact. The discovery of potentially habitable planets and the detection of water has taken that excitement to a new level. Movies, TV shows, books, and video games have all explored the idea of alien worlds and the search for extraterrestrial life. It's become part of our cultural conversation in a way that wasn't true even 20 years ago. But with that excitement comes responsibility. We need to be careful not to sensationalize or oversimplify the science. Headlines like "Scientists find alien ocean" might get clicks, but they can be misleading. The water vapor detected on this exoplanet is not an ocean, and we haven't found aliens. It's important to communicate the science accurately, to explain what we've actually discovered and what it means, without exaggerating or making unfounded claims. That's why scientists, journalists, and science communicators all have a role to play in helping the public understand these discoveries. There's also an ethical dimension to the search for life beyond Earth. If we do find evidence of life, even microbial life, on an exoplanet or a moon in our solar system, how should we respond? Do we have a responsibility to protect that life, to avoid contaminating it with Earth organisms? These are questions that astrobiologists and ethicists are already grappling with. The field of planetary protection, which deals with preventing contamination of celestial bodies, will become even more important as we explore more worlds and develop the capability to travel to them. And what if we find intelligent life? The search for extraterrestrial intelligence, SETI, has been ongoing for decades, but so far we've found nothing. If we ever do detect a signal from an alien civilization, it will raise a host of questions. Should we respond? What should we say? Who gets to decide? These are not just scientific questions. They're political, cultural, and philosophical questions that will require input from people all over the world. The discovery of water on exoplanets brings us one step closer to potentially answering the question of whether we're alone, and that comes with profound responsibilities. Let me also touch on the role of citizen science in astronomy. With the vast amounts of data being collected by telescopes like JWST, professional astronomers can't analyze it all by themselves. That's where citizen scientists come in. Projects like Planet Hunters allow volunteers to search through data for signs of exoplanet transits. Participants have discovered dozens of exoplanets, some of which have been confirmed by professional astronomers. It's a great example of how science can be democratized, how anyone with an internet connection and a passion for discovery can contribute to cutting-edge research. The discovery of water on this exoplanet is also a reminder of the power of international collaboration. JWST is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. Scientists from dozens of countries have contributed to its development and are now using it to make discoveries. In an era where international tensions can be high, space exploration remains one of the areas where countries work together toward common goals. It's a model for how we might tackle other global challenges, from climate change to pandemics. Speaking of climate change, the study of exoplanet atmospheres is also informing our understanding of Earth's climate. By modeling how different gases interact in planetary atmospheres, by studying how temperature and pressure affect atmospheric dynamics, we're gaining insights that are relevant to our own planet. Venus, for example, is a cautionary tale of runaway greenhouse effect. Understanding why Venus turned into a hellscape while Earth remained habitable helps us appreciate the delicate balance that sustains life on our planet. Similarly, studying the atmospheres of exoplanets gives us a broader perspective on how atmospheres work and how they can change over time. Let's also consider the technological spin-offs from space exploration. The development of JWST required advances in materials science, optics, cryogenics, and data processing. Many of these technologies have applications beyond astronomy. For example, the infrared detectors developed for JWST could be used in medical imaging or environmental monitoring. The software algorithms used to analyze JWST data could be applied to other fields that deal with large datasets like genomics or climate science. Space exploration drives innovation, and that innovation benefits society in ways we don't always anticipate. The discovery of water on this exoplanet is also a story about human ambition. We are a species of explorers. From the moment our ancestors first looked up at the night sky and wondered what those lights were, we've been driven to understand the universe. We've built tools to extend our senses, from simple telescopes to sophisticated space observatories. We've developed theories to explain what we see, from the laws of motion to the theory of relativity to quantum mechanics. And we've never stopped pushing the boundaries of what's possible. The detection of water vapor on a world 26 light-years away is the latest chapter in that ongoing story. But let's not forget that exploration comes with challenges. Space is hard. Missions fail. Rockets explode. Instruments malfunction. People make mistakes. The history of space exploration is littered with setbacks and tragedies. But we keep going because the potential rewards are so great. Every failure teaches us something. Every setback makes us stronger. The fact that JWST is working as well as it is, after all the challenges it faced during development, is a testament to human persistence and ingenuity. Now, let's zoom out and think about the big picture. The universe is about 13.8 billion years old. Earth formed about 4.5 billion years ago. Life on Earth emerged relatively quickly, within the first billion years or so. For most of Earth's history, life was simple, single-celled organisms. Complex life, multicellular organisms only appeared in the last billion years. And humans, modern Homo sapiens, have only been around for a few 100,000 years. In the grand sweep of cosmic history, we're newcomers. And yet, in the short time we've been here, we've accomplished remarkable things. We've figured out the age of the universe, the nature of matter and energy, the history of life on Earth. We've sent probes to every planet in the solar system and beyond. We've built telescopes that can see billions of light years into space and billions of years back in time. And now we're beginning to explore other planetary systems, to search for worlds like our own, to ask whether life exists elsewhere. It's an extraordinary achievement, and it's worth pausing to appreciate it. The detection of water on this exoplanet is a small piece of a much larger puzzle. It's one data point among thousands, one world among billions. But it's also a milestone, a sign of progress, a reminder of how far we've come and how far we still have to go. Every discovery builds on the ones that came before. Every question answered raises new questions. That's the nature of science. It's a never-ending quest for understanding. And what about the future of humanity? Will we ever visit these distant worlds? At our current level of technology, interstellar travel is firmly in the realm of science fiction. The distances are too vast, the speeds required too great. Even traveling at a significant fraction of the speed of light, which we have no idea how to achieve, would take decades or centuries to reach even the nearest stars. But that doesn't mean it's impossible. Throughout history, people have accomplished things that were once thought impossible. Maybe someday, centuries or millennia from now, our descendants will develop the technology to travel between the stars. And when they do, the discoveries we're making today will be the foundation for their journeys. In the meantime, we have our telescopes, we have our spacecraft, we have our curiosity and our determination, and we have the universe, vast and full of wonders, waiting to be explored. The exoplanet 26 light-years away, with its water vapor and its alien sky, is just one of those wonders. There are countless others out there, waiting to be discovered. Some might be even more interesting, more Earth-like, more potentially habitable. The search continues. Let me also address something important: the role of skepticism in science. When a discovery like this is announced, it's natural for people to ask, "Are you sure? Could you be wrong?" And the answer is always, yes, we could be wrong. Science is not about absolute certainty. It's about evidence, about building a case based on observations and experiments, about being open to the possibility that new data might change our understanding. The detection of water on this exoplanet is based on strong evidence, on multiple observations, on analysis that has been peer-reviewed by other scientists. But it's also subject to revision if new data comes along that contradicts it. That's not a weakness of science. It's a strength. It's what allows science to self-correct and move closer to the truth over time. There have been false alarms in the past. Claims of life on Mars based on features in meteorites that turned out to be natural, not biological. Detections of exoplanet signals that were later revealed to be instrumental artifacts or stellar activity. These cautionary tales remind us to be careful, to check and double-check our results, to remain skeptical until the evidence is overwhelming. But they also show that science works. False claims don't last long because other scientists scrutinize them, test them, and ultimately reject them if they don't hold up. The discovery of water on this exoplanet has been scrutinized, and so far it's holding up well. There's also the question of what we mean by water. When we say we've detected water on an exoplanet, we're specifically talking about water vapor, H2O in gaseous form. We're not talking about liquid water oceans or solid ice, though those could exist on other parts of the planet or on other planets. Water can exist in 3 states: solid, liquid, and gas, depending on temperature and pressure. On Earth, we're fortunate to have all 3: ice at the poles and on mountaintops, liquid water in oceans and lakes, and vapor in the atmosphere. On this exoplanet, the temperatures are so high that water can only exist as vapor. But that's still water, and it's still significant. The chemistry of water is fascinating in its own right. A water molecule consists of two hydrogen atoms bonded to one oxygen atom, forming a bent shape with an angle of about 104.5 degrees. This shape, along with the difference in electronegativity between hydrogen and oxygen, gives water a polar character. One side of the molecule is slightly positive, and the other side is slightly negative. This polarity allows water molecules to form hydrogen bonds with each other, which gives water its unique properties. It's why ice floats on water, why water has a high boiling point relative to other molecules of similar size, and why water is such an excellent solvent. These properties are crucial for life as we know it. But could life exist without water? It's possible. Scientists have speculated about alternative biochemistries based on other solvents, like ammonia or methane. Titan, Saturn's largest moon, has lakes and seas of liquid methane on its surface. Could there be life in those lakes using methane the way Earth life uses water? We don't know, but it's an intriguing possibility. The search for life beyond Earth isn't limited to looking for water. It's about being open to all possibilities, even the ones that seem strange or unlikely to us. That said, water is still the most promising place to start. It's abundant, it's a great solvent, and we know for a fact that life can exist in water because it does on Earth. Until we find evidence to the contrary, water remains our best bet for finding life elsewhere. The detection of water on this exoplanet, and on many others, tells us that one of the key ingredients for life is widespread in the universe. The question is whether the other ingredients, organic molecules, energy sources, stable environments, are also common enough for life to arise. Now, let's talk about timescales. The universe is old, and things happen slowly on cosmic timescales. A star like the one this exoplanet orbits will live for trillions of years. Earth will be habitable for perhaps another billion years before the sun gets too hot. Human civilization, in its current form, has existed for only a few thousand years. When we think about the search for life and the exploration of other worlds, we have to think in terms of timescales far longer than a human lifetime. The discoveries we're making today are just the beginning. Future generations will build on our work, make their own discoveries, ask new questions. It's a relay race, and we're just one leg of it. There's also the question of how common Earth-like planets are. We know that planets are common, most stars have them. We know that rocky planets are common. They're easier to form than gas giants in the inner regions of planetary systems. We know that water is common. We've detected it on numerous exoplanets and in interstellar space. But how common are planets that are the right size, the right distance from their star, with the right kind of atmosphere, and with liquid water on their surface? That's still an open question. Estimates vary, but some scientists think there could be billions of Earth-like planets in the Milky Way alone. Others are more conservative, suggesting that truly Earth-like planets might be rare. We'll need more data, more observations to settle this question. The discovery of water on this exoplanet doesn't answer that question directly, but it's a piece of the puzzle. It tells us that water can exist on planets of a certain size and temperature. As we observe more planets, we'll get a better sense of how water is distributed, and that will inform our estimates of how many habitable worlds there might be. It's a statistical game in a sense. The more data points we have, the better we can constrain the probabilities. Let me also take a moment to appreciate the beauty of this discovery. There's something poetic about the idea that we can look at a point of light in the sky, a star so faint you'd need a telescope to see it, and from that light alone, deduce that there's a planet orbiting that star and that the planet has water in its atmosphere. It's a triumph of human intellect and ingenuity. It's also a reminder that the universe is knowable. We can figure things out. We can ask questions and get answers. That's empowering. And it's not just about the science. It's about what these discoveries mean for us as a species. They remind us that we're part of something larger, that Earth is one planet among billions, that we share the universe with countless other worlds. They give us perspective on our place in the cosmos. They inspire us to dream, to imagine what might be out there, to wonder if somewhere on some distant world, other beings are looking up at their sky and wondering the same things we are. As we wrap up this journey through the discovery of water on an exoplanet 26 light-years away, I want to leave you with a few thoughts. First, this discovery is just the beginning. JWST will continue to observe exoplanets, and each one will teach us something new. The catalog of worlds we're building is growing every day, and with it, our understanding of the universe is deepening. Second, the search for life beyond Earth is one of the most profound endeavors humanity has ever undertaken. It's a search that spans disciplines: astronomy, biology, chemistry, geology, and more. It's a search that requires patience, persistence, and an open mind. And it's a search that, even if it takes centuries, is worth pursuing because the answer, whatever it is, will change us forever. Third, these discoveries remind us of the importance of science and exploration. In a world full of challenges, climate change, pandemics, political strife, it's easy to wonder if we should be spending time and money looking at distant planets. But science is not a luxury. It's a necessity. It's how we understand the world, how we solve problems, how we improve our lives. And exploration, whether it's exploring the ocean depths or the far reaches of space, is part of what makes us human. It's how we grow, how we learn, how we push the boundaries of what's possible. The detection of water vapor on an exoplanet 26 light-years away is a testament to human curiosity, ingenuity, and ambition. It's a reminder that we live in an age of discovery, an age when we're learning things about the universe that no generation before us could have imagined. And it's an invitation to keep looking, keep searching, keep asking questions. Because out there, among the stars, there are wonders waiting to be found. Worlds with oceans and continents, with weather and seasons, maybe even with life. We've taken the first steps toward finding them, and the journey has only just begun. So the next time you look up at the night sky, think about those distant worlds. Think about the water vapor in the atmosphere of a planet 26 light-years away, molecules of H2O floating in an alien sky, catching the light of a red dwarf sun. Think about the photons that traveled for 26 years to reach us, carrying the chemical signature of water, waiting to be captured by the golden mirrors of the James Webb Space Telescope. Think about the scientists who spent decades building that telescope, the engineers who launched it, the astronomers who analyzed the data. Think about the long chain of discovery that brought us to this moment, from Galileo pointing his telescope at Jupiter to Edwin Hubble measuring the distances to galaxies to the first exoplanet discoveries in the 1990s. And think about what comes next. The planets we'll discover, the atmospheres we'll analyze, the biosignatures we might find. Think about the day, perhaps in our lifetimes, when we detect oxygen and methane together on a rocky planet in the habitable zone, strong evidence that life exists beyond Earth. Think about the day when we point a powerful enough telescope at an exoplanet and see continents and oceans, clouds and storms, a world that's truly like our own. Think about the distant future, when our descendants might travel to these worlds, when humanity becomes a multi-world species, when the dream of exploring the stars becomes reality. All of that starts here with discoveries like this, with the detection of water vapor on an exoplanet 26 light-years away, with the James Webb Space Telescope peering into the infrared, capturing photons from distant worlds, revealing the secrets of alien atmospheres, with scientists working together across borders and disciplines to understand the universe, with the recognition that we're part of something vast and ancient and beautiful, that we're made of stardust, that the atoms in our bodies were forged in the hearts of stars, that the water in our cells might have once been in a comet drifting through the outer reaches of the solar system. This is the story of the universe, and we're part of it. This is the story of water, that simple molecule of 2 hydrogens and 1 oxygen, that essential ingredient for life, found on a world so far away that its light takes 26 years to reach us. This is the story of human curiosity, of our drive to explore and understand, of our refusal to accept ignorance when knowledge is within reach. This is the story of the James Webb Space Telescope, a triumph of engineering and science, a tool that's opening our eyes to the cosmos in ways we never thought possible. And this is just the beginning. The universe is vast, and we've only scratched the surface. There are billions of planets waiting to be discovered, billions of stories waiting to be told. Some of those planets might have water, some might have life, some might have civilizations looking up at their sky, wondering if they're alone, just as we do. We don't know yet, but we're looking, we're searching, we're asking the big questions. And that, ultimately, is what makes us human. Not just the ability to wonder, but the ability to find out. To build the tools, to gather the data, to analyze the results, to share the discoveries with the world. To stand on the shoulders of giants and reach a little higher, see a little farther, understand a little more. The water vapor on that exoplanet 26 light-years away is more than just a scientific discovery. It's a symbol of hope, a reminder that the universe is full of possibilities, that we're not alone in our curiosity, that somewhere out there, other worlds exist with their own stories to tell. It's a bridge between the known and the unknown, between what we've discovered and what we might discover next. It's a testament to the power of science, the value of exploration, and the boundless potential of human imagination. So here's to the James Webb Space Telescope. Here's to the scientists and engineers who made it possible. Here's to the exoplanet 26 light-years away, with its scorching temperatures and its water vapor sky. Here's to all the worlds we've yet to find, all the discoveries we've yet to make, all the questions we've yet to answer. Here's to the journey, the adventure, the quest for knowledge that defines us as a species. And here's to you for taking the time to learn about this discovery, for caring about the universe, for being part of the story. The cosmos is calling, the stars are waiting, and the journey, as always, continues. From the beaches of Earth to the clouds of a distant exoplanet, water connects us all. It's in our bodies, in our oceans, in the atmospheres of alien worlds. It's the molecule of life, the stuff that makes biology possible, the liquid that flows through the veins of our planet. Finding it on other worlds isn't just about the science. It's about understanding our place in the universe, about recognizing that we're part of a cosmic story that spans billions of years and stretches across billions of light years. It's about looking up at the night sky and knowing that we're not just observers, but explorers, participants in the greatest adventure of all, the quest to understand everything. This is JWST Hush, bringing you the stories of the cosmos, one discovery at a time. Thank you for joining us on this journey to a world 26 light-years away, where water vapor drifts through an alien sky, and where the light of a distant star illuminates the beginning of a new chapter in human exploration. Until next time, keep looking up, keep asking questions, and never stop wondering. The universe is vast, and there's so much more to discover. Let's dive deeper into the specifics of this remarkable world and the star it calls home. The host star is classified as an M-dwarf, spectral type M, which means it's cooler and dimmer than our sun by a significant margin. Its surface temperature hovers around 3,000 to 4,000 Kelvin, compared to the sun's 5,778 Kelvin. That might not sound like a huge difference, but in stellar terms, it's enormous. This temperature differential means the star emits most of its energy in the red and infrared portions of the spectrum. If you were standing on the exoplanet's surface, the sunlight would have a distinctly reddish tint, casting everything in hues that would seem alien to our Earth-adapted eyes. The star's luminosity is perhaps 0.1% of the sun's output. Think about that for a moment. This star produces less than 1,000th of the light our sun does. For a planet to be warm enough to have water vapor in its atmosphere, it needs to orbit extremely close to such a dim star. We're talking about orbital periods measured in days, not months or years. This particular exoplanet completes one full orbit around its star in less than 2 weeks. Earth takes 365 days. This planet experiences nearly 26 years in a single Earth year. What does that kind of rapid orbit mean for the planet itself? For starters, it's almost certainly tidally locked. This is the same phenomenon that keeps our moon showing us the same face all the time. When a planet orbits very close to its star, gravitational forces cause the planet's rotation to slow down until it matches its orbital period. One side of the planet eternally faces the star, baked in perpetual daylight. The other side faces away into eternal darkness. There's no day-night cycle as we know it. No sunrise, no sunset. Just an eternal divide between scorching day and freezing night. But here's where atmospheric dynamics become fascinating. If this planet has a thick enough atmosphere, and the detection of water vapor suggests it does, then that atmosphere can transport heat from the day side to the night side. Powerful winds, possibly supersonic, would race around the planet, carrying thermal energy from the sunlit hemisphere to the dark side. The planet wouldn't have the extreme temperature gradient you might expect. Instead, it would have regions of relative temperature stability, though stable is a relative term when we're talking about a world where temperatures could range from hundreds to thousands of degrees Celsius. The atmospheric pressure on this world is another crucial factor we're still trying to nail down. Pressure determines what state water can exist in at any given temperature. On Earth, at sea level, water boils at 100 degrees Celsius. But on top of Mount Everest, where the pressure is lower, water boils at about 70 degrees Celsius. On this exoplanet, if the atmospheric pressure is high enough, water could remain liquid at temperatures that would cause it to boil away on Earth. We're talking about the kind of extreme conditions where the rules we're familiar with get bent into new shapes. The composition of the atmosphere is likely complex. Along with water vapor, there are probably significant amounts of hydrogen and helium, the primordial gases that this planet captured during its formation. There might be carbon dioxide, carbon monoxide, methane, ammonia, and a whole cocktail of other molecules. Some of these we've detected hints of in the spectroscopic data. Others remain speculation until we can conduct more detailed observations. Each molecule in that atmosphere tells part of the story of where this planet came from and how it evolved. Let's talk about the formation history. Planets don't just pop into existence. They're built over millions of years from the disk of gas and dust that surrounds young stars. In the early solar system, this disk was a chaotic place. Dust grains collided and stuck together, forming pebbles. Pebbles accreted into boulders. Boulders smashed together to create planetesimals, objects the size of asteroids. And planetesimals, through countless collisions, eventually built up into planets. For a planet like this exoplanet, a world several times more massive than Earth but smaller than Neptune, the formation process probably involved accumulating a significant amount of gas on top of a rocky or icy core. In the outer regions of the protoplanetary disk, beyond what's called the snow line, temperatures were cold enough for water to condense into ice. This is where planets could accumulate vast amounts of water along with rock and metal. Jupiter, Saturn, Uranus, and Neptune all formed beyond the snow line in our solar system, which is why they're so massive and why their moons are so ice-rich. But here's the puzzle. This exoplanet is now orbiting very close to its star, well inside where the snow line would have been. So how did it end up there? The answer is planetary migration. After planets form, they don't necessarily stay put. Interactions with the remaining disk of gas, gravitational tugs from other planets, and various dynamical processes can cause planets to drift inward or outward over time. This exoplanet likely formed much farther from its star, in a region where water ice was abundant, and then migrated inward to its current position. This migration probably happened early in the planet's history, within the first few million years after formation. As the planet spiraled inward through the disk of gas, it heated up. The water ice on and within the planet would have vaporized, creating the water-rich atmosphere we detect today. It's a violent, dramatic process. Imagine a world moving through space, getting closer and closer to its sun, temperatures rising, ice melting and evaporating, the atmosphere thickening with steam. It's planetary evolution in fast forward. The migration process also raises questions about whether this planet had any siblings. Did other planets form in this system? So what happened to them? Were they ejected into interstellar space during chaotic gravitational interactions? Did they collide with each other? Are they still there, orbiting at greater distances where we haven't detected them yet? These are active areas of investigation. Finding additional planets in the system would give us a more complete picture of its history and evolution. Now let's consider the energy balance of this planet. It receives intense radiation from its nearby star, but it also radiates energy back into space. The balance between incoming and outgoing energy determines the planet's temperature. But it's not a simple calculation. The planet's atmosphere affects how much energy is absorbed and how much is reflected or radiated away. Clouds, if they exist, would reflect some of the incoming starlight. Greenhouse gases like water vapor and carbon dioxide would trap some of the outgoing infrared radiation, warming the planet further. This is where climate modeling comes in. Scientists use sophisticated computer simulations to model the atmospheres of exoplanets. Taking into account all these factors, radiation, atmospheric composition, pressure, winds, cloud formation. These models help us predict what conditions might be like on these worlds. They also help us interpret the observations we make. When JWST detects water vapor, the models tell us how much water there might be, where in the atmosphere it's located, and what that means for the planet's overall climate. The models aren't perfect. They're limited by our understanding of atmospheric physics and chemistry, and by the computing power available to run them. But they're getting better all the time. Each new observation provides a test of the models. When observations match predictions, our confidence grows. When they don't, we learn something new and the models get refined. It's an iterative process, a dialogue between theory and observation. One of the fascinating aspects of studying exoplanet atmospheres is the possibility of detecting clouds and hazes. On Earth, clouds are made of water droplets or ice crystals. But on other worlds, clouds could be made of all sorts of exotic materials. On hot Jupiters, clouds of vaporized rock have been detected. On cooler planets, you might find clouds of ammonia or methane. On this particular exoplanet, if the temperatures and pressures are right, there could be clouds of water vapor high in the atmosphere, or perhaps clouds of more exotic compounds lower down. Clouds affect the spectrum of light we observe. They can mute or obscure the spectral features of gases in the atmosphere. This makes the analysis more complicated, but it also provides additional information. By studying how clouds affect the spectrum, we can learn about the size and composition of cloud particles, the altitude where they form, and the atmospheric dynamics that create them. It's like reading the weather report for an alien world. The presence of water vapor on this exoplanet also has implications for understanding atmospheric escape. Atmospheric escape is the process by which gases in a planet's atmosphere can be lost to space. For planets orbiting very close to their stars, especially around red dwarfs that can be quite active with flares and stellar wind, atmospheric escape can be significant. High-energy radiation from the star can break water molecules apart into hydrogen and oxygen. The hydrogen, being so light, can escape into space, while the oxygen might react with other compounds or also be lost. Over billions of years, this process could dramatically alter the composition of a planet's atmosphere. A planet that started out with a thick, water-rich atmosphere could lose much of its water to space, becoming drier over time. Or, if the planet is massive enough and has a strong enough gravitational grip, it might retain its atmosphere despite the bombardment of stellar radiation. Understanding atmospheric escape is crucial for assessing the long-term habitability of planets around red dwarfs. Red dwarf stars, despite being the most common type in the galaxy, present both opportunities and challenges for habitability. On the one hand, they're long-lived, giving life ample time to evolve. On the other hand, they can be highly variable, especially when young. Red dwarfs are prone to flares, sudden, intense outbursts of radiation and charged particles. A major flare could deliver as much energy to a nearby planet in a few minutes as the planet normally receives in an entire day. If you were standing on the surface during such an event, you'd be fried by radiation. Not a pleasant thought. However, as red dwarfs age, they tend to settle down. The star that this exoplanet orbits is likely several billion years old, past its turbulent youth. It's probably relatively quiet now, though still capable of occasional flares. This is important because it means the planet's atmosphere has had time to reach some kind of equilibrium, rather than being constantly stripped away by stellar violence. The water vapor we detect today might have been there for a very long time. Let's shift gears and talk about the observing strategy that led to this discovery. JWST doesn't just point at random stars and hope to find something interesting. Every observation is carefully planned months in advance. Astronomers submit proposals explaining what they want to observe and why, and a competitive peer review process selects the most scientifically valuable projects. The observation of this particular exoplanet was part of a larger program to survey nearby planetary systems and characterize their atmospheres. The observation itself required exquisite timing. JWST had to be pointed at the star during the brief window when the planet was passing in front of it. A transit. For this planet, with its short orbital period, transits happen frequently, but each one only lasts a few hours. JWST observed multiple transits to build up enough signal to detect the subtle spectral features of water vapor. The more transits you observe, the better your data, the more confident you can be in your results. The data from JWST is publicly available to the scientific community. Once the team that proposed the observation has had time to analyze it and publish their results, typically a year, the data goes into a public archive where any scientist can access it. This openness is a fundamental principle of modern astronomy. It allows independent verification of results, enables new discoveries from data that wasn't specifically collected for that purpose, and democratizes access to the world's most powerful telescope. The analysis of the data is not trivial. The raw data from JWST's instruments has to be carefully calibrated to remove instrumental artifacts and correct for various effects. Then the spectrum, the breakdown of light by wavelength, has to be extracted from the images. This spectrum is compared to models of what you'd expect to see from different atmospheric compositions. It's a process that involves a lot of number crunching and statistical analysis. The detection of water vapor in this case was statistically significant, meaning it's very unlikely to be a random fluctuation in the data. But let's zoom out and consider what this discovery means in the context of other water detections on exoplanets. This isn't the first time we found water on an exoplanet. The Hubble Space Telescope detected water vapor on a hot Jupiter back in the early 2000s. Since then, water has been found on numerous exoplanets of various types. What makes this particular detection special is the combination of the planet's proximity to us, just 26 light-years, and JWST's unprecedented sensitivity and precision. Each water detection adds to our understanding of how common water is in the universe. We're starting to see patterns. Water vapor seems to be common on hot gas giants and hot Neptunes. This makes sense because water is abundant in the cosmos, and these planets are hot enough that any water present will be in vapor form. What we're still searching for is water on cooler, more Earth-like planets. That's where liquid water might exist, and that's where the conditions for life as we know it would be most favorable. The search for liquid water on exoplanets is challenging because liquid water doesn't leave as clear a spectral signature as water vapor. We'd be looking for indirect signs, the presence of water vapor in the atmosphere of a planet in the habitable zone, perhaps, which might suggest oceans below. Or we might look for the glint of reflected sunlight off an ocean surface, though that requires direct imaging of the planet, which is extremely difficult. We're not there yet, but we're getting closer. Another interesting aspect of this discovery is what it tells us about the delivery of volatiles, substances that evaporate easily, to planets. Water is a volatile, so are methane, ammonia, carbon dioxide, and others. In our solar system, the inner rocky planets, Mercury, Venus, Earth, and Mars, are relatively depleted in volatiles compared to the outer planets and their moons. Earth is the exception with its abundant oceans, but even Earth's water content is small compared to the icy moons of the outer solar system. The question of how Earth got its water is still debated. Did it come from asteroids and comets during the late heavy bombardment? Was some water incorporated into the Earth as it formed, trapped in minerals in the building blocks of our planet? The ratio of deuterium to hydrogen in Earth's oceans. Deuterium is a heavier isotope of hydrogen. Provides clues. This ratio in Earth's water is different from the ratio in most comets, suggesting that comets alone can't account for all of Earth's water. Asteroids from the outer asteroid belt have a D/H ratio closer to Earth's oceans, making them a more likely source. For the exoplanet 26 light-years away, the delivery of water would have been part of its formation process. As I mentioned, it likely formed beyond the snow line where water ice was abundant, and then migrated inward. The water we detect today is the remnant of that primordial water supply, vaporized by the planet's proximity to its star. By studying the isotopic ratios of water on exoplanets, if we can achieve that level of precision in our observations, we might be able to learn about the formation history of these worlds in even greater detail. Isotopic ratios are like fingerprints. Different sources of water have different ratios of deuterium to hydrogen, or oxygen 18 to oxygen 16. On Earth, we can measure these ratios in everything from ocean water to ice cores to ancient minerals, and use them to reconstruct Earth's history. Doing the same for exoplanets is a tantalizing prospect. JWST might not have the sensitivity to measure isotopic ratios on this particular exoplanet, but future missions might. Imagine being able to trace the origin of water on a planet dozens of light-years away. That's the level of detail we're aiming for in the coming decades. The discovery also prompts us to think about the diversity of planetary systems. Our solar system has a particular architecture. Small rocky planets close to the sun, gas giants farther out, and beyond them the ice giants. But exoplanet surveys have shown us that this arrangement is just one possibility among many. Some systems have hot Jupiters orbiting closer to their star than Mercury orbits the Sun. Others have multiple super-Earths in tight orbits. Still others have planets with wildly eccentric orbits, or planets in resonant chains where their orbital periods are in simple ratios. This diversity tells us that planetary system formation is a complex, chaotic process with many possible outcomes. The initial conditions, the mass of the star, the composition and structure of the protoplanetary disk, the presence or absence of nearby stars, all affect how planets form and evolve. So do chance events like collisions between growing planets or close gravitational encounters. No two systems are exactly alike, just as no two snowflakes are identical. This exoplanet system might have had a very different history from our solar system. Maybe it formed around a star in a dense star cluster, where interactions with neighboring stars perturbed planetary orbits. Maybe there was a massive collision early in the system's history that changed the trajectories of forming planets. Maybe the disk was particularly rich in certain elements, affecting the types of planets that could form. Each system is a natural experiment, showing us one possible outcome of the planet formation process. Understanding this diversity is important for assessing the prevalence of habitable worlds. If most planetary systems look very different from ours, with hot Jupiters or systems where all the planets are super-Earths, then Earth-like planets in Earth-like orbits might be rare. On the other hand, if systems with small rocky planets in the habitable zone are common, then the chances of finding life elsewhere go up. The statistics are still uncertain, but with thousands of known exoplanets and more being discovered all the time, we're starting to get a clearer picture. Let's talk about the instruments on JWST that made this observation possible. The Near-Infrared Imager and Slitless Spectrograph NIRIS is particularly well-suited for studying exoplanet atmospheres. It can observe transits and capture spectra without the need for a slit, which means it can observe multiple objects simultaneously. For exoplanet studies, NIRISS operates in a mode called Single Object Slitless Spectroscopy, or SOS, which provides high-precision spectra of a single star during a planet transit. The beauty of NIRISS is its sensitivity to the wavelength range where many important molecules, including water vapor, have strong absorption features. The instrument covers wavelengths from 0.6 to 2.8 micrometers, spanning the visible red into the near-infrared. This is the sweet spot for detecting molecules in exoplanet atmospheres. The spectral resolution is good enough to distinguish between different molecules based on the shapes and positions of their absorption lines. Another key instrument for exoplanet studies is NIRSpec, the near-infrared spectrograph. NIRSpec can operate in several modes, including one specifically designed for time series observations like planet transits. It has even higher spectral resolution than NIRISS, which allows it to resolve finer details in the spectrum. For some exoplanets, particularly those with complex atmospheres, NIRSpec's high resolution is essential for teasing apart the contributions of different molecules. Then there's MIRI, the mid-infrared instrument, which operates at longer wavelengths from 5 to 28 micrometers. MIRI is especially useful for studying thermal emission from exoplanets, the heat they radiate into space. By observing a planet as it passes behind its star, an event called a secondary eclipse, MIRI can measure the planet's temperature and detect molecules that have strong absorption features in the mid-infrared, like carbon dioxide and methane. For the water-bearing exoplanet we've been discussing, MIRI observations could provide complementary information about the thermal structure of the atmosphere. The combination of these instruments gives JWST unprecedented capability for characterizing exoplanet atmospheres. Different instruments are sensitive to different wavelength ranges and different types of observations. By using them together, we can build up a comprehensive picture of what's happening in these alien skies. It's like having multiple tools in a toolbox. Each one is designed for a specific job, and together they're more powerful than any single tool alone. The precision required for these observations is staggering. We're talking about detecting variations in starlight of a fraction of a percent. Any instability in the telescope, any drift in the instruments, any unexpected source of noise could swamp the signal we're trying to measure. The engineers who designed JWST had to account for all of this. The telescope is incredibly stable, its temperature is carefully controlled, and its pointing is precise to a tiny fraction of an arcsecond. An arcsecond is 1/3600th of a degree. JWST can point to a fraction of that. It's like hitting a target the size of a dime from 20 miles away. This level of precision is achieved through a combination of hardware and software. The fine guidance sensor continuously monitors the position of guide stars and makes tiny adjustments to keep the telescope pointed exactly where it needs to be. The instruments themselves are designed to minimize internal sources of noise, and the data analysis pipelines include sophisticated algorithms to correct for any remaining systematic effects. It's a marvel of engineering and data science working together. Now, let's consider the broader scientific context. The study of exoplanets is a relatively young field. The first confirmed exoplanet around a Sun-like star was only discovered in 1995. In less than 30 years, we've gone from knowing of no planets outside our solar system to having a catalog of over 5,000, with more being added regularly. And we've gone from simply detecting these planets to characterizing their properties in detail. The discovery of water on this exoplanet 26 light-years away is part of that rapid progression. The pace of discovery has been driven by advances in technology. The radial velocity method, which detects planets by measuring the tiny wobble they induce in their star's motion, was refined in the 1990s to the point where it could detect Jupiter-mass planets. The transit method, which detects planets by measuring the dimming of starlight when they pass in front of their star, was pioneered in the early 2000s and then revolutionized by the Kepler Space Telescope. And now, spectroscopy, the analysis of light to determine composition, is allowing us to study the atmospheres of these worlds. Each method has its strengths and weaknesses. Radial velocity is good for finding massive planets close to their stars, but it's less sensitive to smaller planets or those in wider orbits. The transit method can find planets of all sizes, but only if the orbit happens to be aligned so the planet passes in front of the star from our viewpoint. Direct imaging can potentially find planets at large orbital distances, but it's extremely challenging because planets are so much fainter than their stars. Combining multiple methods gives us the most complete picture. For the exoplanet with water vapor, the initial detection was likely made using the transit method. The planet was discovered because it causes its star to dim slightly when it passes in front. Once we know a planet is there and transits regularly, we can use spectroscopy during transits to study its atmosphere. This is how JWST was able to detect water vapor. It's a beautiful example of how different techniques work together in modern astronomy. The transit method has been incredibly productive. The Kepler mission alone discovered over 2,600 confirmed exoplanets before it ran out of fuel. Its successor, TESS, the Transiting Exoplanet Survey Satellite, is continuing the search, focusing on bright, nearby stars. TESS has found thousands of planet candidates, many of which are excellent targets for follow-up study with JWST. The exoplanet we're discussing might have been discovered by TESS, or by one of the many ground-based transit surveys. What's exciting is that we're entering an era where we can move beyond just finding planets to really understanding them. We can measure their masses and radii, which tells us their density and gives clues about their composition. We can study their atmospheres and learn what gases are present. We can measure their temperatures and map their climates. We can even, in some cases, detect weather patterns, storms, winds, temperature variations between day and night sides. Each exoplanet is becoming a world in its own right, not just a dot in a catalog. This level of detail is transforming planetary science. Before exoplanets, we only had 8 planets, or 9 if you count Pluto, plus their moons to study. That's a small sample size. Now we have thousands of planets, spanning an enormous range of properties. We can study how planet properties correlate with each other and with the properties of their host stars. We can look for trends and patterns that reveal the underlying physics of planet formation and evolution. It's like having thousands of laboratories where we can test our theories. One of the key questions being addressed is, what determines whether a planet becomes rocky like Earth or gaseous like Jupiter? The answer seems to be a combination of factors including the planet's mass, its distance from the star during formation, and the timing of when it accretes gas from the protoplanetary disk. There appears to be a critical mass threshold around 10 Earth masses. Below this threshold, planets tend to be rocky or icy cores with thin atmospheres. Above it, they can gravitationally capture large amounts of hydrogen and helium, becoming mini-Neptunes or gas giants. The exoplanet with water vapor seems to fall into this intermediate category. It's more massive than Earth, but less massive than Neptune. It probably has a substantial solid core surrounded by a thick envelope of gas. The water vapor we detect is part of that gas envelope. Understanding planets like this helps us fill in the gaps in our knowledge. In our solar system, we don't have any planets in this mass range. There's a gap between Earth and Venus, which is similar in size, and Uranus and Neptune. But in other systems, planets in this range seem to be quite common. They might be the most common type of planet in the galaxy. This raises an interesting question. Why doesn't our solar system have a super-Earth or mini-Neptune? Did one form and then get ejected or consumed by Jupiter? Or did the conditions in our solar system's protoplanetary disk somehow prevent such a planet from forming? It's a puzzle that astronomers are actively working on. The answer might tell us something about how unusual or how typical our solar system really is. Let's also talk about the role of computer modeling in interpreting these observations. When we detect water vapor on an exoplanet, we're not directly seeing the water molecules. We're seeing their effect on starlight, the specific wavelengths they absorb. To go from that spectral signature to a statement like, "This planet has water vapor in its atmosphere," requires sophisticated modeling. The models simulate the atmosphere as a series of layers, each with its own temperature, pressure, and composition. They calculate how light would travel through this atmosphere, how it would be absorbed by different molecules, and what spectrum would emerge. Then they compare this theoretical spectrum to the observed spectrum and adjust the model until they match. It's a process of iteration and refinement. The better the match, the more confident we are that our model represents reality. These models have to account for a lot of complexity. The atmosphere isn't uniform. It varies with altitude and possibly with latitude and longitude if there are weather patterns. Different molecules might be concentrated in different regions. There could be clouds or hazes that affect the transmission of light. The temperature structure of the atmosphere, how temperature changes with altitude, has a big impact on the spectrum. All of these factors have to be considered. The computational power required for these simulations is substantial. Running a single model might take hours or days on a powerful computer. And scientists typically run thousands of models with different parameters to explore the range of possibilities and assess the uncertainties in their conclusions. This is where advances in computing have enabled advances in science. 30 years ago, these kinds of detailed atmospheric models would have been impractical. Today, they're routine. Machine learning and artificial intelligence are also starting to play a role in exoplanet science. Algorithms can be trained to recognize patterns in spectroscopic data, to identify the signatures of different molecules, and to flag interesting candidates for further study. AI can also help optimize observing strategies, determining which planets are the best targets based on predicted signal strength and scientific value. As the volume of data grows, JWST will produce petabytes of data over its lifetime. These tools will become increasingly important. But let's not lose sight of the human element. Behind every discovery, every model, every data analysis, there are people. Scientists driven by curiosity, by the desire to understand, by the thrill of discovery. The detection of water on this exoplanet represents months or years of work by a dedicated team. They had to write the proposal to observe the planet, wait for it to be approved and scheduled, monitor the observations to make sure everything went smoothly, download and calibrate the data, run the models, interpret the results, and write up their findings for publication. And the work doesn't end with publication. Other scientists will scrutinize their results, try to replicate them, build on them. That's how science progresses, through a collective effort where each contribution is tested and validated by the broader community. The discovery of water on this exoplanet will be cited in future papers, incorporated into new models, used to motivate new observations. It becomes part of the growing body of knowledge about exoplanets and planetary systems. There's also an educational dimension to these discoveries. Every new finding is an opportunity to inspire the next generation of scientists. Students in classrooms around the world are learning about exoplanets, studying JWST's discoveries, dreaming about what might be out there. Some of those students will go on to become the astronomers, engineers, and data scientists who will design and build the next generation of telescopes, who will discover and characterize new worlds, who will perhaps one day answer the question of whether we're alone in the universe. Public engagement is another important aspect. Discoveries like this capture people's imagination. They remind us that we live in an age of exploration, that there are still frontiers to push and mysteries to solve. Organizations like NASA and ESA do an excellent job of communicating these findings to the public through press releases, social media, visualizations, and educational resources. The images and data from JWST are freely available online, allowing anyone with an internet connection to explore the universe alongside professional astronomers. This democratization of space science is powerful. You don't need to be a professional astronomer to appreciate the beauty of a nebula or the significance of finding water on an exoplanet. You don't need a PhD to wonder about the possibilities of life beyond Earth. These are universal questions that transcend borders, languages, and cultures. They unite us in our shared sense of wonder at the cosmos. Let's return to the science and consider what future observations of this exoplanet might reveal. JWST will likely observe it again, perhaps with different instruments or at different wavelengths, to build a more complete picture of its atmosphere. Scientists might look for other molecules, carbon dioxide, methane, ammonia, that could provide additional clues about the planet's composition and chemistry. They might study the planet at different points in its orbit to see if there are variations in the atmosphere, which could indicate weather patterns or the effects of tidal heating. There's also the possibility of observing the planet's thermal emission directly, not just during transits. When the planet passes behind the star, a secondary eclipse, the amount of light we receive drops slightly because we're no longer seeing the planet's heat. By measuring this drop, we can determine the planet's temperature. We can also get information about how heat is distributed across the planet's surface. Is the hottest point directly under the star, or is it shifted by winds that transport heat around the planet? These details paint a picture of the planet's climate. In the longer term, other missions and telescopes will contribute to our understanding of this and similar worlds. The European Space Agency's Ariel mission, scheduled for launch in the late 2020s, is specifically designed to study exoplanet atmospheres. It will observe a large sample of planets to look for trends and patterns in atmospheric composition. The extremely large telescopes being built on the ground will have the resolution to directly image some nearby exoplanets and study them in unprecedented detail. Together, these facilities will give us a multifaceted view of the exoplanet population. There's also the tantalizing possibility of detecting auroras on exoplanets. On Earth, auroras, the northern and southern lights, are caused by charged particles from the sun interacting with our magnetic field and atmosphere. Similar phenomena might occur on exoplanets, especially those with strong magnetic fields orbiting active stars. Detecting auroras on an exoplanet would tell us about the planet's magnetic field, which in turn tells us about its interior structure and rotation. It's another piece of the puzzle, another way to characterize these distant worlds. The study of exoplanets also intersects with other areas of astrophysics. The composition of planets reflects the composition of the material they formed from, which in turn reflects the history of star formation in the galaxy. Stars create heavy elements through nuclear fusion, and when they die, they scatter these elements into space. Subsequent generations of stars and planets incorporate these enriched materials. By studying the composition of exoplanets, we can learn about the chemical evolution of the galaxy. There's also a connection to the study of brown dwarfs, objects that are more massive than planets but not massive enough to sustain hydrogen fusion like stars. Brown dwarfs have atmospheres with many similarities to those of giant planets, including the presence of water vapor, methane, and other molecules. The techniques developed for studying brown dwarf atmospheres have been adapted for use with exoplanets and vice versa. It's an example of how different fields of astronomy inform and enrich each other. The discovery of water on this exoplanet also has philosophical implications that are worth exploring. The ancient Greek philosophers speculated about the existence of other worlds, but they had no way to test their ideas. Now we can. We can point our telescopes at the sky, gather light from distant stars, and decode the messages carried by that light. We can learn about the chemical composition of worlds we will never physically visit. It's a triumph of the human intellect, a testament to our ability to understand the universe through reason and observation. Carl Sagan, one of the great popularizers of science, spoke eloquently about our place in the cosmos. He called Earth a pale blue dot. When seen from the vantage point of the Voyager 1 spacecraft billions of miles away, that image showing Earth as a tiny speck suspended in a sunbeam was a powerful reminder of our fragility and our insignificance on cosmic scales. But it was also a reminder of our uniqueness. As far as we know, Earth is the only place in the universe where life exists. Finding water on exoplanets, finding potentially habitable worlds, changes that equation. It suggests that Earth might not be as unique as we once thought. And yet, even if there are billions of habitable planets in the galaxy, life itself might still be rare. We don't know how easy or difficult it is for life to arise from non-living matter. On Earth, life appeared relatively quickly, within the first billion years after the planet formed. Does that mean the origin of life is easy, or were we just lucky? It's one of the great unanswered questions in science. Finding even simple microbial life on another world, whether it's a moon of Jupiter or an exoplanet light years away, would help us answer that question. The search for biosignatures, chemical or physical signs of life, is one of the most exciting frontiers in astronomy. On Earth, the presence of large amounts of oxygen in the atmosphere is a biosignature. Oxygen is highly reactive and doesn't persist in an atmosphere unless it's continuously replenished. On Earth, it's replenished by photosynthetic organisms. If we detected oxygen on an exoplanet, especially in combination with other gases like methane that wouldn't coexist in chemical equilibrium, it would be strong evidence for biological activity. But we have to be careful. There are non-biological ways to produce oxygen, such as the photodissociation of water molecules by ultraviolet light. We need to consider all possibilities before claiming to have detected life. This is where detailed atmospheric modeling becomes crucial. We need to understand the planet's environment, its star's radiation output, the chemistry of its atmosphere, and more. Only by ruling out non-biological explanations can we confidently say we've found life. The detection of water vapor on the exoplanet 26 light-years away is a step toward that goal. It shows that we have the capability to study exoplanet atmospheres in detail. It demonstrates that the techniques and instruments we've developed actually work. And it gives us confidence that when we turn our attention to cooler, potentially more habitable planets, we'll be able to detect the gases that might indicate life. Looking ahead, the next decade promises to be incredibly exciting for exoplanet science. JWST is just getting started and will operate for years to come. New ground-based telescopes with enormous mirrors are under construction. Future space missions are being planned. The catalog of known exoplanets will grow into the tens of thousands. And with each new discovery, with each new characterization, we'll get closer to answering the question, are we alone? But even if we never find definitive evidence of life beyond Earth, the search itself is valuable. Pushes the boundaries of technology. It inspires new generations of scientists. It expands our understanding of planets, stars, and the universe. It reminds us that we're part of something vast and ancient and beautiful. The cosmos is full of wonders, and we're privileged to live in an age when we can explore them. The exoplanet with water vapor, orbiting a red dwarf star 26 light-years away, is one of those wonders. It's a world unlike any in our solar system, a world where water exists as superheated vapor in a thick atmosphere, where one side eternally faces the star and the other faces darkness, where winds howl at supersonic speeds carrying heat from day to night. It's alien, inhospitable, fascinating, and it's just one of countless worlds waiting to be discovered and understood. As we continue to observe this planet and others like it, as we build better telescopes and develop better techniques, as we push the frontiers of our knowledge, we're writing the next chapter in humanity's story of exploration. From ancient mariners crossing oceans to astronauts walking on the moon to scientists detecting water on exoplanets light-years away, the spirit of exploration defines us. It drives us to look beyond the horizon, to ask what's out there, to seek answers to the biggest questions. And the questions keep coming. How common are planets with water? How many of them are in the habitable zone? What's the smallest planet whose atmosphere we can characterize? Can we detect seasons on an exoplanet? Can we map the distribution of clouds? Can we find evidence of plate tectonics or volcanic activity? Each answered question leads to new ones. That's the beauty of science. It's an endless frontier. There's always more to learn, more to discover, more to understand. The James Webb Space Telescope, with its golden mirrors and sensitive instruments, is our latest tool for exploring that frontier. The detection of water vapor on an exoplanet 26 light-years away is just the beginning. In the coming years, JWST will observe dozens, perhaps hundreds of exoplanets. It will find water on some, methane on others, carbon dioxide, ammonia, maybe even molecules we didn't expect. Each discovery will be a piece of the puzzle, a data point in the grand survey of exoplanet atmospheres. And somewhere in that data, we might find something extraordinary. A planet with an atmosphere out of chemical equilibrium suggesting active biology. A planet with seasonal variations indicating an Earth-like climate. A planet with a composition that defies our current understanding of planetary formation. The universe has surprised us before. It will surprise us again. So here we are in the year 2024, looking out at the universe with new eyes. The James Webb Space Telescope is showing us things we've never seen before. The discovery of water on an exoplanet 26 light-years away is a milestone, an achievement, a promise of things to come. It's a reminder that the universe is knowable, that with ingenuity and perseverance, we can unlock its secrets. It's a testament to human curiosity, to our refusal to accept ignorance when knowledge is within reach. The journey continues. The telescopes keep watching. The data keeps coming in. And somewhere out there, among the billions of stars in our galaxy, among the countless planets that orbit them, there might be a world with water on its surface, with life in its oceans, with beings looking up at their sky and wondering if they're alone. We don't know yet, but we're looking, and that in itself is remarkable. The molecular physics behind the detection deserves closer examination. When we say that water vapor absorbs infrared light, we're talking about a quantum mechanical process. Molecules aren't static structures, they vibrate and rotate. The bonds between the hydrogen and oxygen atoms in a water molecule can stretch and bend like springs. When infrared light of just the right energy hits a water molecule, it can excite these vibrations. The molecule absorbs the photon, transitions to a higher energy state, and that specific wavelength of light is removed from the spectrum. This is what creates the absorption lines we observe. Different vibrational modes correspond to different wavelengths. Water has three fundamental modes: symmetric stretching, where both OH bonds extend and contract in phase; asymmetric stretching, where one bond extends while the other contracts; and bending, where the HOH angle opens and closes. Each mode absorbs at characteristic wavelengths. The combination and overtone bands, where multiple vibrational transitions occur simultaneously, create a complex forest of absorption lines throughout the infrared spectrum. JWST's instruments are sensitive enough to resolve many of these individual lines, allowing scientists to identify water vapor with high confidence and even estimate its abundance. The temperature of the gas also affects the spectrum. Hotter molecules move faster and rotate more vigorously, which broadens the absorption lines and shifts their intensity distribution. By analyzing the shape and strength of these lines, scientists can infer the temperature structure of the atmosphere. This is incredibly powerful because it means we're not just detecting what's there, but also learning about the physical conditions. The water vapor on this exoplanet exists at temperatures of several hundred to over 1,000 Kelvin, depending on altitude and location. That's hot enough to make the molecules move at speeds of kilometers per second. Consider also the sheer improbability of this measurement. The planet itself is millions of times fainter than its star. We're not directly seeing the planet's light. We're seeing a tiny modulation in the star's light as the planet transits. During the transit, the planet blocks about 1% of the star's light, maybe less. And within that 1%, the additional dimming caused by the planet's atmosphere absorbing certain wavelengths is measured in parts per thousand. We're detecting signals buried in signals, needles in haystacks. The fact that it works at all is a testament to the precision of JWST's instruments and the sophistication of the data analysis techniques. The timing of observations is critical in ways that might not be obvious. Earth's atmosphere, even though JWST is above it, still affects ground-based communications and can introduce noise. The telescope's own thermal environment has to be stable. Any temperature fluctuations could create spurious signals in the detectors. The star being observed has its own variability. Even quiet stars have granulation on their surfaces, convection cells like Earth's thunderstorms but far larger, which create tiny brightness variations. All of these effects have to be accounted for and removed from the data to reveal the subtle signature of the planet's atmosphere. There's also the challenge of cosmic rays. In space, high-energy particles constantly bombard the telescope's detectors, creating brief flashes of signal that look like bright pixels in the images. A single cosmic ray hit during a critical moment of an observation could corrupt the data. The solution is redundancy and statistics. Multiple exposures are taken, cosmic ray hits are identified and flagged by comparing images, and the affected data is discarded. It's painstaking work, but necessary to ensure the integrity of the results. The discovery of water on this particular exoplanet also illuminates the role of archival astronomy. Not all discoveries come from brand new observations. Sometimes, valuable science emerges from reanalyzing old data with new techniques or new questions in mind. The data from JWST, once public, will be mined for years by scientists around the world. Someone might look at this planet spectrum and notice a subtle feature that wasn't mentioned in the original paper. Someone else might develop a new atmospheric model that better explains the observations. The data keeps giving long after the initial discovery is published. Let's talk about the statistical significance of the detection. In science, we don't just claim we found something because we think we see it in the data. We need to quantify how confident we are. This is done using statistics. Scientists calculate the likelihood that the observed signal could have arisen from random noise rather than from a real physical effect. If that likelihood is very small, typically less than 1 in 1,000, then we say the detection is statistically significant. For the water vapor on this exoplanet, the significance is high. Multiple independent absorption features, all consistent with water, seen across multiple transits with consistent strength. It's a robust detection, but science is conservative, and rightly so. Even with a high significance detection, the possibility of systematic errors remains. What if there's an unknown instrumental effect that mimics the absorption signature of water? What if the star itself has water vapor in its outer atmosphere that we're confusing with the planet's atmosphere? These scenarios are unlikely, but they have to be considered. Independent observations with different instruments, or observations of the planet with ground-based telescopes, help confirm the finding. The more lines of evidence that point to the same conclusion, the more confident we become. The economics of space exploration plays a role that's often overlooked. JWST cost $10 billion to develop and launch. That's a staggering sum, equivalent to building several dozen large hospitals or funding tens of thousands of college scholarships. People legitimately ask, is it worth it? The answer depends on what we value as a society. The direct economic return from astronomy is hard to quantify, though technological spin-offs do occur. But the knowledge gained, the inspiration provided, the advancement of human understanding, these have value too, even if they don't show up in a quarterly earnings report. Publicly funded science has to justify itself to taxpayers, and astronomers take this responsibility seriously. They communicate their findings, they engage with schools and communities, they show how their work connects to broader questions about our place in the universe. The discovery of water on an exoplanet might not cure cancer or solve climate change directly, but it contributes to a culture that values knowledge, that sees understanding the universe as a worthy goal. And that culture, in turn, supports all of science, including medical research and environmental studies. The international nature of JWST is also significant. NASA led the project, but the European Space Agency contributed major components, including the near-infrared spectrograph and the mid-infrared instrument. The Canadian Space Agency provided the fine guidance sensor and the near-infrared imager and slitless spectrograph, the very instrument used to detect water on this exoplanet. Scientists from dozens of countries are part of the research teams using JWST data. It's a model of international cooperation, showing that space exploration can bring nations together in pursuit of common goals. In an era of geopolitical tensions, this cooperation is valuable in its own right. Scientists from countries that might have fraught diplomatic relations still collaborate on research papers, attend the same conferences, peer review each other's work. Science transcends politics because the laws of physics are the same everywhere, and the pursuit of truth is a universal value. The discovery of water on an exoplanet is the result of this global scientific community working together. Let's shift to thinking about what makes a planet potentially habitable. We often focus on water, but water alone isn't sufficient. You need a source of energy, typically starlight, though internal heat from radioactive decay or tidal forces can also work. You need the right chemical elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, the building blocks of life as we know it. You need stability, a planet where conditions don't change so rapidly that life can't adapt. And you need time, millions or billions of years, for evolution to do its work. This exoplanet fails several of these criteria. It's too hot, too close to its star, probably tidally locked with extreme conditions. But it teaches us about the range of environments that exist. And it reminds us that habitability is a spectrum, not a binary. There might be environments where microbial life could survive even if complex life couldn't. There might be niches, high in the atmosphere where it's cooler, or in subsurface regions shielded from radiation, where conditions are more favorable. Europa and Enceladus, moons in our own solar system, are good examples. Their surfaces are frozen and inhospitable, but beneath the ice, there are oceans of liquid water kept warm by tidal heating. If life exists there, it would be in those subsurface oceans, not on the surface. Similarly, an exoplanet that seems uninhabitable at first glance might have regions or layers where life could survive. We need to think creatively about where to look. The concept of the habitable zone itself is evolving. The traditional definition is the range of distances from a star where liquid water can exist on a planet's surface. But this definition makes assumptions that the planet has an Earth-like atmosphere and pressure, that there's a solid surface, that water is on the outside rather than underground. A more sophisticated approach recognizes that habitability depends on many factors, and that planets outside the traditional habitable zone might still harbor life. Tidal heating is one mechanism that expands the possibilities. When a planet or moon is in an elliptical orbit, or when it's caught in a gravitational tug-of-war between its star and another planet, the changing gravitational forces cause its interior to flex and heat up. This can keep water liquid even far from the star where sunlight is weak. Io, Jupiter's innermost large moon, is the most volcanically active body in the solar system because of tidal heating. Europa and Enceladus also benefit from this process. Could there be exomoons around distant planets where tidal heating creates habitable conditions? It's possible, and it's something astronomers are thinking about. Atmospheric composition also matters. A planet with a thick carbon dioxide atmosphere might experience enough greenhouse warming to keep water liquid even at distances where an Earth-like atmosphere would result in a frozen surface. Venus is an extreme example of the greenhouse effect run amok, but a more moderate version could expand the habitable zone. Conversely, a planet with little atmosphere might be frozen even in the traditional habitable zone because there's no insulation to trap heat. The study of extremophiles on Earth has expanded our understanding of where life can survive. We found microbes living in boiling hot springs, in the frozen Antarctic in acid mine drainage, in the deep ocean near hydrothermal vents, even kilometers underground in solid rock. Life is tougher and more adaptable than we once thought. This gives us hope that even in environments that seem hostile, life might find a way. The question isn't just, does this planet have liquid water? But could any form of life survive there, given what we know about life's adaptability? The discovery of water on this exoplanet adds one more data point to our understanding of atmospheric chemistry. Why does this planet have water vapor when others might not? Is it because of the planet's formation history, its mass, its distance from the star, or some combination of factors? As we study more planets, patterns will emerge. We'll be able to say things like, planets with masses between X and Y tend to have water-rich atmospheres, or water vapor is more common around stars of certain types. These empirical relationships will, in turn, inform our theoretical models of planet formation. There's also the question of how atmospheric composition changes over time. A young planet might have a very different atmosphere than an old one. Early Earth's atmosphere had no free oxygen until photosynthetic organisms evolved and started producing it. Mars once had a thicker atmosphere and liquid water on its surface, but lost most of it over billions of years. The exoplanet we're studying is probably billions of years old, so its current atmosphere is the result of a long evolutionary process. Understanding that process requires studying planets of different ages around stars of different ages. The field of comparative planetology is enriched by every new exoplanet we characterize. We can compare hot Jupiters to each other and ask why some have certain molecules in their atmospheres while others don't. We can compare super-Earths to determine what makes one rocky and another gaseous. We can look at how atmospheric properties correlate with stellar properties. The more examples we have, the more robust our conclusions become. It's like how having a large sample size in a medical study gives more reliable results than a small sample. Now let's consider the impact of stellar activity on habitability. Red dwarf stars, especially young ones, can produce powerful flares that bathe nearby planets in harmful radiation. High-energy ultraviolet and X-ray photons can strip away atmospheric molecules and damage biological molecules like DNA. For a planet orbiting as close as this one does, stellar activity is a major concern. However, a thick atmosphere can provide some shielding. The upper layers of the atmosphere absorb the high-energy radiation, protecting the layers below. Magnetic fields also play a protective role. Earth's magnetic field deflects charged particles from the solar wind, preventing them from stripping away our atmosphere. A planet with a strong magnetic field could maintain its atmosphere even in the face of intense stellar activity. Detecting magnetic fields on exoplanets is extremely difficult with current technology, but it's an area of active research. If we could determine which exoplanets have magnetic fields, it would greatly improve our ability to assess their habitability. The star that this exoplanet orbits is relatively old and quiet, which is good news for atmospheric stability. Over the billions of years since the planet formed, it's had a chance to establish an equilibrium. The water vapor we detect today is probably similar to what was there millions of years ago, and what will be there millions of years from now, barring any catastrophic events. This stability makes the planet a good laboratory for studying atmospheric chemistry and physics. Let's talk about what happens when results from different telescopes or instruments disagree. Sometimes, one telescope detects a certain molecule in an exoplanet's atmosphere, and another doesn't. This can happen for several reasons. The instruments might be sensitive to different wavelength ranges, so one sees absorption features that the other doesn't. The observations might be taken at different times, and the planet's atmosphere might have changed, perhaps due to weather or seasonal variations. Or there might be systematic errors in one dataset that weren't fully accounted for. Resolving these discrepancies is how science advances. When results disagree, it forces scientists to dig deeper, to re-examine their assumptions, to look for sources of error. Often, the resolution involves better understanding the instruments or refining the atmospheric models. And sometimes, the disagreement reveals something genuinely new about the planet. Maybe the atmosphere really does change over time in unexpected ways. These are the kinds of puzzles that keep scientists engaged and excited. The role of theory in guiding observations cannot be overstated. Before JWST observed this exoplanet, theorists had already modeled what its atmosphere might look like. They predicted that water vapor should be present based on the planet's mass, temperature, and formation history. The observations confirmed those predictions, which is satisfying but also somewhat expected. What would be really interesting is if we found something the theories didn't predict, an unexpected molecule, or an abundance that doesn't make sense given our current models. That would be a sign that we're missing something, that there's new physics or chemistry to discover. The interplay between theory and observation is the engine that drives science forward. Theories make predictions. Observations test those predictions. When observations match predictions, our confidence in the theory grows. When they don't, we revise the theory or develop a new one. Over time, through this iterative process, our understanding becomes more accurate and more complete. The detection of water vapor on this exoplanet is one turn of that cycle. We should also acknowledge the role of serendipity in scientific discovery. Sometimes, the most important findings come from observations that were intended to study something else entirely. A scientist looking for one thing might notice an anomaly in the data that leads to a completely different discovery. The history of astronomy is full of such examples. Pulsars were discovered accidentally by a graduate student studying something unrelated. The cosmic microwave background, one of the most important discoveries in cosmology, was found by engineers trying to eliminate noise from a radio antenna. With JWST producing vast amounts of data on diverse targets, the potential for serendipitous discoveries is high. Someone analyzing the spectrum of this exoplanet might notice a faint feature that wasn't expected, leading to the discovery of a new molecule or a new atmospheric phenomenon. Or someone studying an entirely different target might stumble upon something unexpected. The data archives are treasure troves waiting to be explored. Let's zoom back in on the specific characteristics that make this discovery noteworthy beyond just the presence of water. The planet's proximity to us, 26 light-years, means it's one of the nearest worlds where we've characterized the atmosphere. This makes it an ideal target for follow-up studies. It's bright enough in the sky that observing it doesn't require enormous amounts of telescope time. Other telescopes, both space-based and ground-based, can also study it, providing complementary data. It's become a benchmark system, a reference point for understanding hot Neptunes. The 26 light-year distance also has a psychological impact. It feels close, even though it's still an unimaginably vast distance by human standards. If we could travel at 1,000,000 miles per hour, far faster than any spacecraft we've ever built, it would still take over 17,000 years to get there. And yet, compared to the scale of the galaxy, it's right next door. This juxtaposition of the familiar and the alien, the nearby and the unreachable, captures something essential about our relationship with the cosmos. Thinking about future human exploration, even if interstellar travel seems impossible now, we shouldn't assume it will always be so. Breakthroughs in physics could change the game. Concepts like fusion propulsion, antimatter engines, or even more speculative ideas like warp drives or wormholes are currently in the realm of theoretical physics. Some might remain forever impossible, constrained by fundamental laws of nature, but others might become feasible with sufficient technological advancement. Our descendants hundreds or thousands of years from now might look back on our era the way we look back on the age before aviation, when people thought flying was impossible. Even if we never achieve faster-than-light travel, generation ships, spacecraft that travel for centuries with multiple generations living and dying aboard, are theoretically possible with known physics. You'd need a propulsion system capable of reaching a significant fraction of light speed, robust life support systems, and a self-sustaining ecosystem aboard the ship. It would be an enormous undertaking, but not necessarily impossible. For a destination 26 light-years away, a ship traveling at 10% of light speed would take 260 years to arrive. Long, but within the span of human institutions like universities or religions that have lasted for millennia. But these are dreams for the distant future. For now, our exploration of this exoplanet and others like it happens through photons, through the light that travels across the void to reach our telescopes. We are explorers in the truest sense, pushing the boundaries of knowledge even if we can't physically travel to these worlds. Every observation is a voyage. Every spectrum is a journey to an alien world and back. The discovery process itself has been democratized in recent years. Amateur astronomers have contributed to exoplanet science by monitoring known transiting planets, helping to refine orbital parameters and even discovering new planets in public data. Citizen science projects allow volunteers to classify light curves, search for transits, and flag interesting candidates for professional follow-up. This crowdsourcing of science leverages the power of thousands of eyes and minds, and it gives people a direct connection to the process of discovery. Educational institutions are also using exoplanet data in curricula. Students can analyze real JWST data, learning about spectroscopy, atmospheric physics, and data analysis while working with cutting-edge observations. This hands-on approach to science education is powerful because it shows students that science isn't just about memorizing facts from textbooks. It's about exploring the unknown and making discoveries. Some of those students will go on to become the next generation of astronomers and engineers. The cultural impact of exoplanet discoveries extends into art, literature, and philosophy. Science fiction has long imagined alien worlds, but now we have real examples to inspire new stories. Artists create visualizations of exoplanets based on scientific data, trying to capture what these worlds might look like. Philosophers contemplate the implications of finding life elsewhere, questioning how it would affect our understanding of humanity's place and purpose. These interdisciplinary conversations enrich both science and culture. As we approach the conclusion of this journey through the discovery of water on an exoplanet 26 light-years away, let's reflect on what it all means. This single discovery is a thread in a much larger tapestry. It's part of humanity's age-old quest to understand the cosmos, a quest that began when our ancestors first looked up at the stars and wondered what they were. For most of history, those questions had no answers. The stars were mysteries, objects of worship and speculation, but not understanding. The scientific revolution changed everything. Galileo pointed a telescope at Jupiter and saw moons orbiting it, proving that not everything revolves around Earth. Newton formulated the laws of motion and gravitation, showing that the same forces that make apples fall also keep planets in their orbits. Spectroscopy revealed that stars are made of the same elements found on Earth. The scale of the universe expanded with each generation, from the solar system to the Milky Way to billions of galaxies stretching across billions of light-years. And now, we're characterizing the atmospheres of planets around other stars. We're detecting water, the molecule of life, on worlds scattered throughout our galactic neighborhood. We're asking whether Earth is unique or one among countless inhabited worlds. These are questions that would have seemed like pure fantasy to scientists just a century ago. Yet here we are doing it. The James Webb Space Telescope represents the culmination of decades of work by thousands of people. It's the result of advances in engineering, optics, cryogenics, computer science, and countless other fields. It required international cooperation, sustained funding, and a shared vision of what could be achieved. The fact that it exists at all, that it works as brilliantly as it does, is a testament to human capability when we set ambitious goals and work together to achieve them. The water vapor detected on this exoplanet 26 light-years away is more than molecules in an alien sky. It's evidence that the universe is comprehensible, that we can decode its secrets through observation and reason. It's a reminder that we're part of a cosmic story much larger than ourselves, a story written in atoms and energy across billions of years. It's proof that the same chemistry that makes life possible on Earth operates throughout the universe, suggesting that life itself might be a cosmic imperative rather than a terrestrial accident. Every generation faces the question of what to leave behind, what legacy to pass to those who come after. The discoveries we make today are part of that legacy. The data from JWST will be preserved for future generations to study and reanalyze with techniques we haven't invented yet. The knowledge we gain about exoplanets will inform the missions and telescopes of the 2030s, 2040s, and beyond. We're building a foundation, laying groundwork, asking the first questions that will lead to deeper questions in the future. The search for life beyond Earth is one of the great adventures of our time. Whether we find it in our lifetimes or whether it takes generations more, the search itself ennobles us. It represents hope, hope that we're not alone, that consciousness and intelligence might be common features of the universe rather than rare flukes. It represents curiosity, the drive to explore and understand that defines us as a species. And it represents humility, the recognition that Earth is one small world among billions, that we're newcomers in a cosmos far older than we can fully comprehend. The exoplanet with water vapor reminds us that the universe is full of worlds we're only beginning to discover. Some are hellish, some might be paradises, most are probably strange in ways we haven't imagined. Each one is a natural laboratory where the laws of physics and chemistry play out in unique ways. Each one teaches us something about how planets form, evolve, and perhaps give rise to life. Our sample size is growing from 8 planets to thousands, and with it, our understanding deepens. As you think about this discovery, water vapor on a world 26 light-years away, detected by a telescope orbiting 1,000,000 miles from Earth, analyzed by scientists around the globe, remember that you're witnessing history. This is the era when humanity took its first real steps toward understanding the nature and prevalence of planets beyond our solar system. This is when we began to seriously ask whether life exists elsewhere and developed the tools to find answers. Future generations will look back on this time with the same sense of wonder that we feel when reading about Galileo's first telescopic observations or Darwin's voyage on the Beagle. The cosmos is calling us forward. Every discovery raises new questions. Every answered question opens new mysteries. The detection of water on this exoplanet is not an ending but a beginning. The beginning of detailed atmospheric characterization, the beginning of a catalog of worlds with diverse chemistries, the beginning of the search for biosignatures that might reveal life beyond Earth. We stand at a threshold. Behind us is the history of astronomy, from ancient stargazers to pioneering telescope builders to the scientists who first detected exoplanets. Ahead of us is a future where we might answer the question that has haunted humanity since we first became aware of the stars. Are we alone? The water vapor on a planet 26 light-years away is a signpost pointing toward that answer, whatever it may be. In the end, this discovery is about connection. Connects us to the universe in a direct, tangible way. The same atoms that make up that distant planet's water vapor are found in our oceans, in our bodies, in every glass of water we drink. We are literally made of stardust, and so is everything else in the universe. The hydrogen in water was forged in the Big Bang. The oxygen was created in the heart of a star that exploded billions of years ago. That star's death gave birth to new stars and planets, including the one we're studying now, and the one we call home. This is our story. This is humanity's journey from wondering about points of light in the sky to understanding them as worlds with atmospheres and chemistry and perhaps life. It's a journey powered by curiosity, enabled by technology, and united by our shared desire to know. The discovery of water on an exoplanet 26 light-years away is one step on that journey. But what a magnificent step it is. The universe is vast beyond comprehension. Contains more stars than grains of sand on all of Earth's beaches. Around those stars orbit countless planets, each with its own story, its own characteristics, its own mysteries. We've taken one planet, one small world in that immense cosmic ocean, and learned something fundamental about it. We've detected water vapor in its atmosphere using light that traveled for 26 years to reach us. If that doesn't fill you with awe, check your pulse. So here's to the scientists who built JWST. Here's to the theorists who predicted what we might find. Here's to the observers who collected the data and the analysts who decoded it. Here's to everyone who has ever looked up at the night sky and wondered. And here's to the exoplanet itself, 26 light-years away, with its scorching temperatures and its water vapor sky, teaching us about the diversity of worlds and the unity of chemistry across the cosmos. The exploration continues. The questions multiply. The universe beckons. And we answer, not with spaceships yet, but with telescopes and instruments and the boundless power of human curiosity. We are a species that looks up and wonders, that builds tools to extend our senses, that refuses to accept ignorance when knowledge is possible. The water vapor on that distant world is proof that our reach, if not yet our grasp, extends to the stars. This is what we do. This is who we are. Explorers, questioners, seekers of truth. The detection of water on an exoplanet 26 light-years away is another chapter in the greatest story ever told, the story of the universe itself, and our place within it. The chapter is just beginning. The best discoveries may still lie ahead. And somewhere out there, among the countless worlds we've yet to find, there might be one where water pools in liquid oceans, where chemistry gives rise to biology, where evolution crafts complexity from simplicity, where other beings look up at their sky and wonder the same things we do. We don't know yet if that world exists, but we're looking. And the fact that we can look, that we have the capability to search for water on planets light years away, that we're asking these profound questions and developing the means to answer them, that itself is extraordinary. It's a triumph of the human spirit, a celebration of what we can achieve when we aim high and refuse to be limited by what seems impossible. The universe is ancient. It will exist long after we're gone. But in this brief moment, this cosmic eye blink in which humanity exists and looks outward, we're learning its secrets. We're mapping its geography. We're cataloging its worlds. We're searching for life. And in doing so, we're discovering not just what's out there, but who we are. We are the universe aware of itself, matter contemplating matter, stardust pondering stardust. The water vapor on an exoplanet 26 light-years away connects us to that larger reality. It reminds us that we're part of something vast and magnificent. It shows us that the chemistry of life extends beyond Earth. It proves that our tools and our methods work, that science delivers on its promise to reveal nature's truths. And it inspires us to continue to build better telescopes, to ask deeper questions, to never stop exploring. This is our legacy. This is our contribution to the ages. Long after our buildings crumble and our names are forgotten, the knowledge we're gaining will endure. It will be built upon by future generations, expanded and refined, woven into an ever more complete understanding of the cosmos. We are privileged to live in this age of discovery, to witness these breakthroughs, to participate in this grand adventure. So the next time you look up at the night sky, remember, out there, just 26 light-years away, is a world with water in its atmosphere. We've never seen it with our eyes, but we've detected it with our instruments. We've measured its properties and characterized its environment. We've added it to our growing catalog of known worlds. And somewhere out there, beyond what we've discovered so far, there are countless other worlds waiting. Some with water, some with other wonders, perhaps some with life. The cosmos is full of mysteries, and we're solving them one photon at a time. The journey from ignorance to understanding is long, but we're making progress. Each discovery is a victory, each answered question a cause for celebration. The detection of water vapor on this exoplanet is one such victory. It won't be the last. The universe has more secrets to reveal, and we're ready to discover them. This is humanity at its best. Curious, ambitious, collaborative, reaching beyond our earthly confines to touch the infinite. The stars are no longer just points of light. They're suns with planets, worlds with atmospheres, possible homes for life. We're beginning to know them, to understand them, to see them not as distant, unreachable objects, but as places, as real as Earth itself. And so we continue. The telescopes keep watching. The data keeps streaming in. The scientists keep analyzing, modeling, interpreting. The story unfolds, chapter by chapter, discovery by discovery. Water on an exoplanet 26 light-years away. It's a simple fact, 3 H2O molecules in an alien sky, but it represents so much more. It represents progress, possibility, and the enduring human drive to explore and understand. The universe awaits. The answers are out there, written in starlight, encoded in spectra, waiting to be read by those with eyes to see and minds to comprehend. We are those beings. We are the readers of cosmic messages, the decoders of nature's secrets, the explorers of the infinite. This is our time. This is our moment. And the discovery of water on a world 26 light-years away is proof that we're equal to the challenge, ready for the adventure, worthy of the cosmos we inhabit. Keep looking up. Keep asking questions. Keep pushing the boundaries of what we know, because out there, among the billions of stars and trillions of planets, wonders await. And we, curious, persistent, ever-reaching humanity, we're going to find them.